interested in getting into the intersection where creativity in architecture and courage meet, our next presenter is the right one for you. So I'd like to kind of introduce Joshua Ramus. He will present two very, very interesting showcases to us. Thank you very much for joining us. Welcome.
Great, thank you. Thank you all. First, is the sound okay? Credit where credit is due. There's so many people in this audience who are consultants, contractors, subcontractors, whose intelligence and inspiration has profound impacts on the design solutions that we all collectively as architects explore. So I need to acknowledge front, because the two projects that I'm going to present are intense collaborations between our two firms. Critical naivete. This is the notion within our office, the way we describe it, of returning back to first principles and exploring them with a child's mind. All of us who have children know that children are in fact naive, but that does not mean they lack any criticality, particularly in a pandemic. And that criticality leads them to see and advance ideas that sometimes absolutely shock us. And it's within that spirit that I want to show two projects in which the end results are things we simply couldn't have conceived before, initially or individually, and led to solutions that not only delight us, but then had pretty profound impacts on things that we explored subsequently. The first project is for a fashion company in Istanbul. By the way, the initial introduction said this was all about New York, and I'm going to show two projects, one that's in Istanbul and one that's in Washington, D.C. So my apologies for being not New York focused. Project for the fashion company Vaco in Istanbul. And we were approached by the CEO to take the bones of a hotel that had never been completed, it started 25 years before, and convert it into his headquarters in a matter of less than 1 year. Now, at the outset, that might seem like an absurd request, but it just so happened that as he was showing us the image of this, what I knew in the back of my mind, we had done a project for Caltech in which there was this very sturdy braced frame in the center of the building, and around it was a super lightweight post-tension concrete slab structure that was being held up by that internal braced frame. The project had been shelved when Caltech's leadership changed. And when looking at the structure that he presented us with, it became apparent that it was exactly the same dimension as that lightweight perimeter concrete shell. So we started the project, we flew to Istanbul, arrived there on a Tuesday morning, we met with his engineers, we figured out ways to take the detailing that we already had for the Caltech project and apply it to this hotel. And that allowed them to start construction, or at least demolition, on Friday. Now we had 6 weeks from that moment until steel installation had to start, and that meant that we needed to provide the mill order within 2 weeks. The problem that we were confronted with was the inverse of Caltech. So we had this wildly over-designed, and by the way, we're going to get to facades in a moment. In each of the projects, I think it's important to give the background of the project to understand the context of the enclosure solution. The problem was actually the inverse. Here we had a wildly over-designed structure. We didn't have any analysis, we didn't have the drawings, we didn't know how it would perform. There wasn't the ability or time to do any kind of forensic analysis. And it was within that that we actually had to design all of the more specific programs of his project, as well as all the vertical circulation. So it became a lightweight steel structure that would move independently of the thing on the outside that we simply didn't know really how it would perform. To meet the steel mill order, we divided the program up into clear organizational boxes. We sent the steel mill order out after 2 weeks. We then started to figure out how to combine those boxes in different ways to meet all of the internal circulation requirements. These are the studies. And then when the steel showed up on site, we said, okay, fabricate it this way. And that's literally what they did. So this is what we call the showcase. There you see it sitting in the center of the concrete rings, sort of like Alien popping out of the chest of Cain. God, that usually gets a laugh, but I guess not at this morning on a... Anyway. And they literally fabricated the boxes in the site adjacent to the project, picked them up in toto and just submerged them into the center of the building. So this is the first 4, then there's 5, then there's 6 and 7. And that diversity led to something that had also an almost like urbanistic qualities. You move through the building, that each one of these boxes had a very tailored architectural response based on the needs of the things that were within it. This is all just sort of eye candy, but to get to the point of the facades. It just happens that the showcase was wrapped in a kind of insane mirror glass. These are actually undoctored renderings, images of the interior of the building. Fashion company, so it is full of female and male models, and so part of the internal humor of the project was that they would then be replicated thousands of times throughout the... Okay, so facade enclosure. I said we had this lightweight steel structure, sort of moved independently of a much heavier concrete object that we didn't really fully understand how it would perform, and needed to clad it. And there was a second thing going on during the discussions of the design of the enclosure, is that our client, very much inspired by precedents around the world, wanted somehow to have his brand imprinted on the facade of the building. I'll be honest, it was not something that we felt very comfortable. If you know anything about our practice, that's not really who we are. And I'll come back to that later, because I think we found a solution that delighted both, or say, appeased both of us in the process. That structure, not only do we not know how it would perform, we also knew that as architects, as much as we might want to obliterate it, and I don't mean demo it, I mean make its present not overt, I think we acknowledged quite early on in the process that was never going to happen. And so instead we proposed to lean in, to say, hey, this is an important moment in which can't we show that we can make capital A architecture out of an existing structure, a form of adaptive reuse? And that was actually something to be proud of, and he should embrace that. And with that idea, we said, why don't we not attempt to subvert the presence of the existing hotel structure, but actually, if we can wrap it in a super thin saran wrap, can we actually reveal it? Can we make it part of the important expression of this brand's ethos and its commitments to sustainability? The idea then was, could we slump a geometric shape that improved its own structural integrity, increases its moment of inertia, such that we could thin the glass and remove any kind of vertical mullions. And this is going to become a theme between the two projects that I'm describing. And the ultimate idea, because the simplest way that we could affix this onto that heavy concrete structure with a simple pin connection, was to slump giant X's into the facade. This is an idea that we could only do in Istanbul at that moment. Simply, if you attempted to do this in the United States now or even then, it would be cost prohibitive, and there are a whole host of reasons why it would never be viable. There it was viable because in Turkey, in the late aughts, there was a huge diaspora of Turkish contractors that had moved into Western Europe. And over that, from the early 90s through to the late aughts when we started this project. And that diaspora had become wildly technically sophisticated. And then they had come back and brought all of that technology into Turkey at the moment that Turkey also had, while it was aging, a remarkable craftsman class. And so we could combine these two sort of optimal things into one moment in which we had the ability to make very, very sophisticated jigs that were going to be destroyed. Each one of these jigs lasted maybe 2 panes, sometimes 3, but the craftsmen were able to make them over and over and over again with incredible precision, and frankly, the labor was wildly inexpensive. And at the same time, they had all kinds of very sophisticated equipment that allowed them to selectively cool and control the cooling of the slumping process in order to make something that was kind of an idealized of those two opportunities. And so it's through that process that we created what we started to call saran wrap. There you see some of the first panels that were fabricated. And then it went on to the exterior of the building. So this is the moment where I tie the initial observation back into the desire to express his brand onto the face of the building. The name of the company was Vaco. I hope he is not listening to this on the live stream, but what we presented originally was none of anything I just said to you, but it was simply Vaco, 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 all over the facade. It met his desire of expressing his brand in a kind of similar way I had shown of Coach and other brands, Yves Saint Laurent. But it met the kind of aspirations that we had originally of building the opportunity out of sort of the contextual environment of Istanbul in that moment. Here you see the glass. And then full disclosure, we did not finish it in the original 11 months that was requested. We failed and we did it in 14. And that's the final iteration of it. So the second project I want to show is very much an intellectual evolution of the first. It's a project for Tishman Speyer in Washington, D.C. Washington, D.C., similar to Berlin, has a very draconian zoning environment in which effectively you simply have to build out to the property line and to the height. It's just to make an office building economically viable. It creates a rather homogeneous urban experience. It has nothing to do with actually seeing the Capitol building from all vantage points. That's the mythology. It's very much about just bringing light and air into the streetscape. And historically, DC is full of heavy masonry buildings, from Beaux-Arts to neoclassical to Art Nouveau to Brutalist. All of them are have the quality of having punched openings, a lot of relief in the facade. Obviously, they are masonry of different forms. And now we're seeing injected into that environment a whole slew of taut, skinned glass, floor-to-ceiling glass buildings that kind of feel uncomfortable in the environment. They don't know what to do because that environment has a lot of bas-relief, a lot of depth. They don't. And so what you're seeing is like a proliferation now of these buildings coming up in which they then get added to their skins aesthetic elements in order to give that relief. To be honest, in most instances, I don't know what else to do either. The invention was, okay, again, the client had tasked us with creating the new standard of Class A office space, whatever that to mean. And we defined it as floor-to-ceiling glass, as thin a glass as we could actually produce, and the elimination of any kind of vertical mullion in order to eliminate any kind of view-impeding elements. Largely why? Because, as I said, there wasn't much else to do within the DC zoning envelope. Right? We had to be almost like a balloon, like blow up to the limits of the envelope. And so the observation was very much carried over from the Vaco headquarters, is that if we could give it a subtle curvature, increase its moment of inertia and its stiffness, we could reduce the thickness of the glass and we could eliminate any kind of vertical mullion whatsoever. Now, where it was possible to do the slumped form that I had shown in Istanbul in 2009, obviously that would not be possible in the United States in 2018 and 19 when we produced the building. But the idea has all the advantages of the strength of curved glass combined with a unitized system, but it took advantage of new innovations in bending tempering furnaces. So while the systems that we know as slump forming used to take, in this case these are metal jigs so that they don't get destroyed, was cost prohibitive for us in Istanbul, while this would take 10 hours to produce a single light. We're now in a situation in which a single light of curved glass, if that's what you're focused on, can take 10 seconds. And so it reopened up an opportunity from a cost standpoint to explore this idea in the US market. The project can be subsumed down into literally just two details, a kind of standard, typical, and a corner. It effectively, because we've eliminated the structural mullion component, it's effectively just a very simple unitized frame that, I say simple, Obviously, it took a lot of engineering to get to that point, but a very simple unitized frame in which we take all of the sort of proprietary detailing and compress it into that very discrete 2 elements. It's base supported, it's not a curtain wall. And there you see the implication of taking that, just those 2 details and replicating. And that was effectively the promise that we made to Tishman Speyer in the beginning is, have courage that we can take just those 2 details, replicate it, and we'll create something that is, we hope, sublime. Just show some of the renderings, the photography of it. And there you see from the interior, the idea of eliminating the structural element and having only this very, very reduced aesthetic frame. The initial detailing actually didn't have that at all, and to their credit or critique, Tishman Speyer at some point said, no, we want to actually have this very sort of thin, unitized frame. I think it probably saved all of us an enormous amount of headache through the process. And it made something that had appropriate relief within that context of Washington, D.C., with all these heavy masonry punched opening buildings. There's a combination of a pyrolytic coating and a soft low-E coating on the interior of the IGU that creates this kind of remarkable kaleidoscopic effect. And then this is the image that I always show to say enjoy our client, our main client at Tishman Speyer, Rustam Kawisji. When we initially presented this, the property line actually is at the flat surface that you see there. Under the DC zoning, you can actually extend over the property line by a maximum of 4 inches in what is called an architectural detail, a flourish. And our observation was that if we restrained or we defined the curvature to hit that 4-inch mark, what was interesting is that we could gain this tiny amount of leasable area. Now, I think in the end it totaled about 492 square feet, so I don't think it really had much of an economic impact. But Rustam, as a true developer, couldn't get over the concept of like sticking it to the man, that he was getting an extra 500 square feet on this project. And I sometimes think that was the motivator that got them over the intellectual relief to go on this journey with us. I am obsessed with Mies, as are many of the people probably here and elsewhere, in attempting to meet one of his early study models and the idealized sort of vacant corner. The slabs of the building taper. They're all a post-tension concrete slab system. They taper to 8 inches. The columns have been recessed 12.5 feet. And so combined with this incredibly thin, therefore transparent glass with wildly slender substructure, it actually achieved something very similar to that early ideal, something that has inspired us for years in our own exploration. So I'm now going to talk about what I think is maybe the most important lesson that we learned out of the project. When we presented this project in competition, we didn't just present the design. We knew that if we presented the design, this is a sophisticated client, they would probably laugh us out of the room. So we presented the design and we presented a procurement strategy. And they selected the design and the procurement strategy. The procurement strategy was the following, that we would create a pre-validated prescriptive design. Now, be clear that in the end, the project was still, final engineering was still assigned to the facade subcontractor. But we pre-validated the glass, we pre-validated the frame and the support. We then, the first act was to separate the glass from the frame and the support. All with the idea of, in order for the client to feel comfortable moving forward, we would need to validate 2 things. We need to validate the optical clarity, the performance of the glass optically, and that we would have to be able to know that the price could meet their overall budget. And so with that in mind, we let the glass to 5 different potential glass fabricators around the world, and they were to produce glass samples, and we prescribed the actual frame that would go on, as well as started giving us pricing. And so so here you see the frame, and these are the different prototypes that were produced by those 5, all of them extremely capable glass suppliers. This is the one that we ultimately went with from North Glass. What was remarkable was that the initial pricing we received back from these 5 very capable glass subs was an order of 2 to 1. Okay? And it just emphasizes why there is the importance of the value of taking through the procurement process and separating the systems out, is we started to reveal the inherent underlying tensions that are always happening when we're just bidding an entire system, and we don't really know, is it the cost of the glass, is it a preference of a glass fabricator that a facade sub wants, is it something else? Basically, we have no way of dissecting and understanding what's driving price. Now it's all exposed out into the open. I think some of you probably in the room don't like this concept, but for us, as people trying to validate an idea and to give our client the best design, the best glass, the best price, it was incredibly important. And so Tishman had, when we presented the initial idea, the one thing we asked of them in the competition presentation was, if you take this project on, you need to agree now to pre-purchase the glass. Tishman Speyer did it. So they negotiated the glass with the best optical quality that we had, the best, the people who produced the best samples, got the best price, they pre-purchased it, and then that glass was novated ultimately to the successful facade sub. Then, after that was done and we started to produce the glass, we then let the facade frame and the facade support system. Again, so it meant that now when we were getting prices competitively, it was only based on the proprietary details of that frame and support, not anything to do with the glass system itself. The glass itself. And that was the end result of that. I can't tell you the price, but I can tell you that it was not wildly above commodity curtain wall. And just as a side note then, we created this, we're going back now just into pure architecture, as a counterpoint to this crystalline facade that some people I think could maybe criticize as being a bit uptight. The lobby of the building goes in completely opposite direction. It's incredibly central as a combination of an onyx and sapwood mahogany. And then the curvature, that subtle, it's a 9'6" radius, then appears throughout the building. Sometimes you can see here, as well as with the stone as detailing on the interior of the building that goes not only adjacent to the facade, but even in elements that you see as in the washrooms. Thank you.
Thank you very much. That was great. And we are taking no offense on you buying the glass separately from the aluminum system. So in the order of some time saving, we will go to our break. And instead of 20 minutes, we'll do 15 minutes. So we would be expecting you back 5 after half, 11:30. Yeah.
two, 1, 2. 1, 2, 1, 2. 1, 2. 1, 2, 3, 4, 5, 6. 1, 2. Test. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 1, 2, 1, 2. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
for the next presentation. If you would please get seated, everybody. We are ready for the next interesting topic.
मतलब इसका हाँ मालूम है हाँ हाँ हाँ
सबके नए प्रेजेंटेशन
हाँ मालूम है मतलब वो you connected everything at once.
Okay, while everybody is seated, I
I'll manage.
will go ahead and introduce our next speaker. He will be talking to us about embodied carbon reduction, a topic that has been very popular in our industry, and I think it's one of those topics with the most misunderstandings that we would have about it. So our next speaker is Rowan Georges from SOM. Thank you very much for joining us, Rowan.
Thank you very much. It's great being with so many colleagues who I have not seen in quite some time. And I was explaining to them it's kind of hard to follow what preceded this morning, being that I'm a spec writer. So I'll try to follow with what I hope is an interesting topic for us all. So in framing this discussion that I will lead today, we all know the dire situation that we're in. And this first image evokes that challenge. And a few years ago, SOM established a client action group. And for some context, that client action group was in direct response to what's happening currently in the world, this global crisis that we have to contend with. And so they came up with 10 design principles that are outlined here as a plan of action for SOM, or as I would put it, an intervention rather than a plan of action at this critical juncture. Each of these principles is correlated. Each of these principles also have their own distinctions, but altogether they clarify the firm's position as an intentional path forward to address this global crisis. Today's talk will be centered on facades, but we'll touch on at least 2 of the 10, but we should be thinking of them all. And for some context, SOM's Climate Action Group also gave way to our technical design group in coming up with, well, how do we put these 10 design principles into practice? How do we accomplish, how do we achieve these goals? And this past summer, our leadership of our technical design group globally took necessary steps in advancing our design practice to ensure that we keep ourselves on target with what the Climate Action Group set forth in the 10 design principles. So we established these 5 firm-wide working groups to keep us on target to achieve these goals: designing low embodied carbon enclosures, designing for zero operational carbon, designing with timber and bio-based materials, designing for passive house, and finally designing for breathable buildings. For expediency's sake, we'll only focus on obviously the first one, but these again are 5 topics in which you'll see a continual thread in these designs of SOM. In order to further frame this discussion, we'll focus on what we know, or more importantly, what we don't know. We'll focus on what tools we have available to us as a practice, what tools we have available as an industry, and what have we done, and what have we done, and what will we be doing more of to help us implement these goals? How will they be implemented? We all know the dire situation. We all know that we're long overdue in addressing this critical issue of carbon emissions. So here's what we know so far. Just how big of a problem is this? 3.8 billion tons of carbon emitted every year. Design excellence must equate to outstanding environmental performance. It should not be an afterthought. It ought to be embedded in our DNA as designers. It ought to be embedded in our DNA as owners, fabricators, manufacturers. We all are in this together. We need to understand how to strike this delicate balance between environment, materiality, and performance. And I might get in a little bit of trouble by saying this. We all need to be open and transparent about our processes. We don't have all the answers. We'd like to share what we have in the hopes that you would share what you have so that we could all do this together. Here are some things we don't know. We don't know quite yet how to effectively select alternative materials with low embodied carbon emissions while considering operational carbon. How will these processes be integrated and executed? How do we approach our clients? Some are far more advanced than others. And how much will these interventions really cost? Working at SOM, we have expertise in the realm of sustainable engineering, and our partner, our principal for sustainable engineering, Luke Leung, he said, Rowan, make sure you focus on whole life carbon. I know you're going to a facades conference, but we cannot consider facades only. We have to consider the whole life carbon. It requires a trade-off. Talk about, we cannot isolate components if we're speaking the language of zero carbon emissions. We can't just focus on operation energy savings. We have to take a holistic approach. SOM has done studies on more passive envelopes and the reduction to energy, and more importantly, the refrigeration reduction that show the industry has to work on a different paradigm moving forward to look at the entire building holistically and not components in isolation. So here's the challenge. How can we as an industry, how can we as architects understand this trade-off between low embodied carbon and low operational carbon when it pertains to facades? And how can we use that knowledge to inform our designs? I'm going to walk you through a few of the iterations, a few of the tools that we and resources that we as a practice have been engaged in the last few months. Sitting next to me today was a gentleman from Dublin who was representing one of these software engineering tools. So these are some of just a handful of tools that we've studied many. We're actually doing research and innovation into optimizing which tools will work best for our practice. But these are some of the tools that are available to us in the industry. And of course, being SOM, we came up with our own tool because that's just what we do. And so in-house, we've created this SOM EC 101 tool, which we developed in collaboration with our climate action group. Now, this is designed to be used at the earliest conceptual phase of the project, where you can input as much information as you can. And as the project further develops, those inputs are then refined. But the important message here, the storyline here, is to get it done as early as possible so that you're thinking about embodied carbon as the project goes through its process. Here's one project that was done by our Chicago office, still in design at this time, located in Shanghai, where we examined low embodied carbon in terms of what it meant for the facade. In this first slide, we're showing that the impact of embodied carbon as being related directly to the window-to-wall ratio. So really, fundamentally, the higher the window-to-wall ratio, the lower the embodied carbon. But at the same time, the higher the window-to-wall ratio, it also equates to higher operational carbon. And so, like Luke Leung would remind me, we've got to learn how to strike this delicate balance, and that's key to understanding. And embodied carbon savings is to be balanced with operational consumption in addition to this payback period that we're seeing here. Carbon payback period informs our design choices. When do we use shading devices? And if we do use shading devices, what type of material should we be using? What is the payback period? And so all these are considerations that can be made early on in the design process. Here's another example. This was from our San Francisco office for a project in Taipei, Taiwan. Currently has just finished design development. In this project, when we analyzed the facade, the low embodied carbon of the facade, these are the values that we're coming up with in the initial stages. And so this project has recently completed design development, and these are currently only estimates of what the embodied carbon will be in the facade. So we're able to leverage tools such as Revit and Rhino for the more complex geometries, and then we export that data into the EC101 tool, and we can estimate at an early stage of the project the GWP outputs as the design develops. Now, once we've used the Revit model, each of the components can be quantified. We can quantify the volume of glass, we can quantify the volume of aluminum, and then we can take the target GWP values from the database that we have and plug those numbers in, and as the design advances, these components are further and further refined. So outlining here is a process of exactly what I just described, but to make it simple for spec writers like me, this image is more telling. We use everything that we have available to us to come up with that target GWP number, but what's most important and what's most valuable and what I want to encourage today with transparency, especially with the partners that have sponsored us today, is this collaboration. We cannot do this without collaboration from manufacturers and fabricators. So we're saying that we want to get involved with you as early and as often with you as possible. So as we take the conceptual design level, here in this image we're showing some mullion profiles that we might come up with very early on. And as the design develops, we can further refine the profiles, and we can apply reduction factors that are based on our experience and hopefully based on the collaboration that we have with you, the fabricators and the manufacturers, and we can establish GWP values for the profiles as the project advances. And we'll do the same for glass, right? We start off with a glass that we like, and then we will work with the fabricators to come up with the right coatings, the right thickness for optical, but also making sure that the glass that is selected is one that has low embodied carbon. So here's what we know so far in this project, that we've evaluated the systems, the profiles that meets the design intent. We've evaluated preliminary embodied carbon for aluminum and for glass, and the Revit model is accurate for the design. What we still need to do at this juncture is now complete the embodied carbon analysis by analyzing things such as thermal breaks, insulation, sealants, etc., and also finish the specification, and that's where I come in, and then back check, do a QA/QC analysis of our embodied carbon calculations, either by third party or by a consultant. A little bit closer to home, this is a confidential project in Cambridge, Massachusetts, and this project was all about this closed cavity facade, south-facing facade, and boasting of a PEUI of 51 kBTU per square foot per year. In this project, SOM explored more advanced and more sophisticated and higher technology to diligently balance energy, carbon, views, daylights, etc. And the client fell in love with this ultra high performing shingle glass facade. So we explored various facade typologies. We explored standard double IGU. We explored triple IGU, ventilated cavity facade, and we finally settled on the closed cavity facade as it met our design objectives for performance. And for context, this closed cavity facade, it's south facing, while the other facades employ a more traditional curtain wall system. But as beautiful and as technologically advanced as this facade is, a closed cavity facade also means that there's a lot of glass. And lots of glass in this system, while performance-wise is great, carbon emissions is something with which we have to strike that delicate balance. And so by using our own SOM EC101 tools, we've estimated that we're coming up with some GWP estimates that for the facade components that are in the 17 to 18% range for the facade components. We're actually in real time meeting later today with Arup, our sustainable design consultant, to go over the LCA analysis. Everything that I'm discussing right now is in real time because this is an ever-evolving part of our industry. When we meet with Arup later today, we'll want to ensure that we're meeting our LCA assumptions, and I'm sure we'll have lots more balancing to do once we get there. A little bit more closer to home here in New York City, here's another confidential project, this time for a health science laboratory in the city. Now, laboratories, they typically consume 4 to 5 times more energy than similarly sized commercial space. But here in this project, what we can boast of is an almost 80% reduction. The client's sustainability goals were driven primarily by energy savings. This was a top priority. And so by boasting of this 80% reduction in energy costs as compared to baselines for similarly sized lab buildings, this was a wonderful intervention. In terms of the facade itself, the podium consists of a terracotta-clad podium and this upper glazed volume where the labs themselves are located. Now, this glass volume is organized around a structural digrid optimized for transparency. But also of note here is the program for the lab spaces themselves in this upper glazed volume warranted that they be stacked 2 floors each. And so the stepping south facade is responding to that program requirement, stepping back every 2 floors. So we've also leveraged this stepping down design to utilize as inherent shading strategies for the south facade. We do employ aluminum diagonal shading devices, but we optimize the depths of the shading devices based on the solar demands. So in this south facade, you will find deeper depths of 14 inches as opposed to 4 inches on the other sides. We just want to only use it where we need it. What other resources do we have? The resources that we have at our fingertips right now include research, innovation, but more importantly, collaboration with you. Collaboration with you, our industry partners. Here in this image, we've recently been in conversation with a company called Hydro in Europe. We've been in recent conversation about their very low embodied carbon aluminum that's currently on the market in Europe. These products boast of the lowest GWPs that we've seen thus far. And the question remains, how soon can we see this type of low embodied carbon aluminum reach its way to North America? That's a challenge for the folks in the room today. Similarly, in the glass industry, we're seeing things like broken and rejected glass being added into new materials. With these glass cullet melts they melt at a much lower temperature than sand. It's recyclable. It reduces overall needs. And so this is something that we're taking a hard look at, and we're pushing our friends from Guardian. We're pushing our friends from the glass industry to get better in terms of embodied carbon. Side note here, in terms of what's available in North America, the curtain wall manufacturers, the commercial manufacturers, they also have EPDs where we're taking a look at some of the values and how those stack up with some of our modeling. So we talked about knowledge, we talked about resources, but how do we implement? How do we bring everything together? How do we put all the pieces of the puzzle together? Implementation must begin with training. At SOM, we're training all of our staff, from the partnership level all the way down. Everyone is speaking the same language when it comes to lowering embodied carbon. Training also should incorporate owners, developers, contractors, fabricators, manufacturers. We all need to be speaking the same language. Here's some real numbers that we've done as a global practice, and I'll just list two building types. So we've examined embodied carbon by building types, and here on the screen we're seeing we can get these values for commercial and residential buildings. But we've also examined embodied carbon by element, by construction assemblies. How much carbon is in your foundation? How much carbon is in your structural system? And as we see where facades are concerned, we want to reduce from the 16% range all the way down to 8%. We think we can do it, but we need your help. When speaking the language of reducing carbon, we also need to speak the language of circular economy as opposed to what we're used to in a linear economy, where repair, reusing, remanufacture, recycle is part of this economy, part of the language that we speak when it comes to facades. How do we implement these low carbon strategies in general terms? Very, very simply, we select materials that are made to last. We need to select materials that require very minimal maintenance. We need to engage, as I've said before, all of our fabricators, our manufacturers, engage in things like design assist processes to optimize the embodied carbon. We need to use less material. Less is more, reducing the size, reducing the complexity, embracing manufacturing sizes. SOM is infamous for making custom sizes. We need to embrace what is standard, and if we're going to do that, we have to push the manufacturers to making sure that standard sizes are optimal. Reduce waste, prefabrication, reuse through recycled content or repurposing. How do we employ this in a facade? Simplify your facade panels. Minimize them, optimize them. Optimize performance by climate zone. And of course, use low carbon materials. The strategic use and the selection of insulation types by application, and also reducing the amount of metal that we use for our facades. Remember that the metals that are not seen, those also count towards your carbon. So aligning material life cycle costs and maintenance with building. And here are just some values that we've come up with through our research. Aluminum is a very interesting story. What we're showing here on the screen are very aggressive numbers, 5.580 to 6.670 kilograms per CO2. Why are we being so aggressive? We're being so aggressive because aluminum, as we all know, is the largest contributor to the CO2 emissions out of all of the industries. It's one of the most energy-intensive materials that's produced. And so what we're finding is that there is availability for higher recycled content. We've taken a look at some of the industry-wide EPDs. Here on the screen, what we're showing is the Aluminum Association. That's the number that we think we can get to at 6.57. The ICE database is higher. We're trying to understand exactly why it's higher. And I apologize for the graphics. They're a little screwed up here on this monitor. The Aluminum Extruders Council came out with their industry-wide EPDs this past July, and we've documented here what those values are. They took a slightly different approach where they examined mill finish versus painted finish, and of course, extruded, thermally improved aluminum would be higher if you count in all of the things that make them thermally improved. But what we're interested in is the raw aluminum data on the right. Similarly, glass, these are some numbers that we are targeting for low embodied carbon. Steel, okay, we're requiring higher recycled content in steel, standardizing some of the connections. And of course, one of my favorite materials, concrete, okay, strategic cement content to really hit those target numbers. Wood, timber, it just goes hand in hand with the whole discussion on low embodied carbon. With sequestration, we can get to these negative values. We're seeing a lot more buildings with wood. I'm very excited about the Zak World of Façades conference on timber. I hope I get invited to that as well. We're no strangers to wood SOM. When I first joined the practice about 16 years ago, this was what we were doing for the U.S. Census Bureau. Obviously, with wood comes the challenge of maintenance, and so if we can do it there back, 16 years ago, we should be doing more of it now. And here's just a side-by-side comparison of your facade materials in terms of the low embodied carbon numbers that we're targeting. Similarly for other metals. And now to the good part. As a spec writer, I just love text, so if you would indulge me for a moment. 2 years ago, SOM, in response to the SOM Climate Action Group's commitment, we pledged that we would decarbonize all of the materials in our specifications. And so this was a 2-year research effort that spanned all the offices around the globe. And in these specifications, what we're targeting, or what we're putting as requirements in those specifications, are the lower embodied carbon targets. We're going to be favoring suppliers that produce low embodied products. We're pushing the limits, pushing the boundaries of recycled and biodegradable content and clean energy sources for manufacturing processes. How are we doing that? We're asking for these as submittals. I want to be very clear. We're not asking for them as sustainable design submittals. We're asking for them as submittals. They're inherent. So whether or not a project is going for LEED or BREEAM, we're asking for these submittals. Not only are we asking for the submittals, we're listing the target GWP values in the specification. Obviously, there are some challenges that come with that, since some industries are lagging behind others. But what we are doing is we're sending out letters to all the manufacturers in our specifications, highlighting them to the fact that we're doing this and giving them a date by which they need to comply. Otherwise, they will be removed from the specification. I know you can kill me later, but we have to do something, and we have to do it now. So what's next? I think doing our buildings with low embodied carbon materials is the bare minimum we should be doing. We could be doing more. We can be exploring other materials like hempcrete, biocrete, biobrick, and of course timber, as we've spoken about. All of these are nature-based materials that can not only low embodied in terms of what they are, but they can also absorb carbon over time. And guess what, guys? They're commercially available. So I challenge all of our partners in the room with me today. How can we collaborate with you to develop smart facade systems to take advantage of these systems on a larger scale? Just last week at the COP26, SOM unveiled Urban Sequoia. Urban Sequoia is this proposition that the built environment can absorb carbon, as we move the conversation from simply lowering embodied carbon to actually absorbing carbon and making carbon work for us, SOM's proposal transforms buildings into viable solutions by radically rethinking how buildings and cities are designed and constructed. It's a viable solution that could have a far-reaching impact with the potential to create a circular economy that absorbs carbon. With that, I close and I say thank you.
Thank you very much, Rowan. That was quite a wake-up call. Thank you, appreciate that. The one thing that is beautiful about Europe, and I think a lot of you would agree, there's a lot of small to medium-sized companies with capabilities and specialties that we would not find here in the US. The next presenter is one of the owners of this company called Hofmann Façades that is specializing in natural stone, but also has a profound understanding of composite materials such as high performance, ultra high performance concrete, and the combination of it, if we just put this together with what Dan taught us today about opaque surfaces, is creating a very, very interesting topic. We are very happy to have Philipp Hofmann here, managing partner of Hofmann Façades, who will be talking to us about decarbonizing facades. Thank you, Philipp.
Thank you. Thank you. Good afternoon, everybody. So good to see so many people in person again here. Just wanted to start with this. And we heard it already this morning. It is about opaque components in the facade, materiality, and foremost embodied carbon, not the operational carbon. We also have to be honest in this dialogue. There's a lot of greenwashing, putting lipstick on a pig. That's why I really am trying to be very objective now, what I deliver to you. And thank you, Owen, for this excellent presentation before. There was one material missing, though, I have to tell you. It was stone. So you talked about a lot of aluminum and others, but not stone. Therefore, I am going to show you today something that's already available today. So it's not a concept or an idea for tomorrow, but it's something that's available today that you can all use. And as we all are responsible in this, as stakeholders in this industry, to adopt designs, to make them more carbon friendly, to really make the material the key element of architecture again, and not just try to force materials that cannot perform in a way that they're intended into old architecture. We have developed something that I'm going to present to you today, which we call the Carbon Navigator, and that really gives you an overview as a matrix of facade system and materials across the board, and expresses a embodied carbon level in kilograms per square meter, so that each of you designers and specifiers has some guidance for that. But before I go there, let me also quickly refresh your memory why this climate crisis, this dramatic climate crisis is so urgent. We cannot wait to delay this to the future. So from all the carbon that's in the atmosphere, 50% was only added since 1980. That means it was us, maybe our parents. But this has been done by us in our generation. Our industry is a major, major culprit in that. Aluminum was mentioned, but by volume, cement is actually the single largest carbon emitter. And if it was a country, it would come right after China and the United States as an emitter. So 33 billion tons of carbon are emitted every year. The industrialized nations, including China, are leading by far. And you saw this earlier. To really help you put this better in perspective, I put this as a very tangible example for New York. So if every second 2 tons of carbon are emitted in New York, this is what it will look after 1 hour, piling up these spheres, after 1 day, and after 1 year. And you cannot see New York anymore. That's how sad this is. So to reduce this pile, we have to really look where this comes from, and there is some trends, unfortunately, underlying this that makes this dilemma even more dramatic. It is the share of building operations and new construction is actually rapidly rising due to growing population on the planet. We're going from 7.5 to 10 billion people. There's more and more urbanization. That means more and more people are moving to cities. That means there's more construction. With more construction, there is more energy need for these buildings, and there's more emissions. So this is not something that's going to go away by itself. We are adding about every 2 months the size of the city of Greater London for the next 35 years. That's what is being forecasted as a construction volume outlook. And maybe some of you know this, but I didn't, so I was quite surprised. Carbon does not dissipate fast. 40% are still there after 100 years, and even 10% after 10,000 years. That means this is not going to resolve itself. And even if we stop emitting carbon completely today, we still have to deal with the sins from the past. The consequences, both in severity as well as in frequency, are increasing from bushfires in the US to floods and inundations in Germany, heat waves that kill people, or even dried out lands in India, or hailstorms in Mexico. This is a very, very clear indication. So for anybody who thinks, is there a correlation between human behavior and climate change, it is scientifically proven by now. There was the 1.5 Celsius Paris Accord. We are already far above that. We currently, this was the outcome of COP26 at 2.7 degrees Celsius. That's what we're tracking. And there is a Potsdam study that actually looks at climate domino effects, how all these weather patterns can actually influence each other and make it worse and accelerate it. So I just want you all to be aware this can tip off very quickly, which is why I cannot believe that we are glorifying architecture like something like this, which has a water use of 250,000 gallons a day, or 50 million watts of maximum draw. It's just insanity. It's like a little power plant just for this building. And then the chasing higher and higher in the sky also has to stop. This is not sustainable, especially in this climate zone. So, as Charles Dickens says, the age of foolishness, maybe we're in it, but we all don't want 2150 to look like this. Therefore, I'm going to stop now painting a gloomy picture. There's a lot of positives. There was this climate conference in Glasgow that just ended. For the first time, they had dedicated an entire day to the built environment, made some really good goals and results. Carbon trading as a global standard is introduced. A cement maker from Germany, which was actually, and this is now governments imposing on industry, Heidelberg Cement was almost forced to shut down their cement plant in Sweden. And out of the pure need to come up with an innovative approach, they created a carbon capture, carbon sink approach, where they are now actually going to lower the amount of carbon that they're putting in the atmosphere, not increasing it. So this is all a result of regulatory pressures and change of mind. New York, we heard about Local Law 97, a wonderful initiative that really penalizes people if they don't live up by that, but it's heavily focused, obviously, on the operational carbon and energy efficiency. London as well has the London Energy Transformation Initiative, or shortcutted LETI, that has set very specific carbon targets, both embodied carbon and operational carbon targets. But what is very important to understand, and I cannot stress this enough, as we get more and more efficient MEP systems, the share of the operational carbon gets larger, and with that, its importance rises. And we do not want to offset carbon by LCA calculations in 50, 60 years from now, when our grandchildren are dealing with this. We want to do this today. So whatever we can take care of today, we don't have to offset tomorrow. So this calculated or calculative greenwashing, which I call some of these LCA models, have really to stop, and we have to lower embodied carbon, because that's the only thing that matters today. The material is produced today that goes on the site, and even if the building performs well over its life cycle, it is important that we look at low embodied carbon products. There is a Bloomberg building in London that was rated under BRIM, which is the British LEED rating, the highest rated office building in the world. It is a complete exuberance of steel, heavy concrete, the foundations are oversized, so this could have been equally energy efficient on its operational carbon, but it could have been way more improved on the embodied carbon side. And so there is now, weightings are changing in LEED and BRIM, and people are starting to think how to shift those credits to really incentivize the use of better materials. We saw this before. The embodied carbon makes about 50% of a building's carbon footprint. Of that, the facade can be 16%, 20%. It ranges on the architecture and building shape, but it is a very large portion after the superstructure. Obviously, the building envelope influences the operational carbon heavily. And now let me go into this navigator. Oh yeah, thank you. So, as I mentioned, cement is, and where does all the emissions come from in the construction materials? And this was not mentioned in the prior presentation. It is energy, it is heat that is required. So almost every single material that we use on a building as a facade material requires heat. May it be brick or terracotta, or ceramic that requires sintering, or steel that requires cooking, or aluminum that has to be molten, or limestone that gets killed to become cement, the calcium in cement. That all requires heat. But there is a product that is readily available everywhere on this planet that nature provides already finished, and it's natural stone. There is zero heat required to make natural stone. It is readily available. You can cut it out of the mountain. You can 100% recycle it, and you can process it with very low energy. Yeah? We even have hydropower and solar in our facility, so we use zero non-renewable energy to process the stone. And it is so ubiquitous. The entire lithosphere of our planet, other than water, is made out of stone. So 90% of the solar surface of the Earth are natural stone, which is why it's available everywhere. And it is a renewable material because the entire Earth's core is liquid magma, and most of the granite is actually crystallized volcanic material. So you haven't seen this, but this puts now all the materials that are used on facades and on buildings in reference to one another. We heard how bad aluminum is. It is 175 times the embodied carbon of stone. Even cement is still about 13 times, and glass 12.5 times. Even brick is 3.5, or terracotta 4.5 times. Ceramic is actually very bad, so sorry for the ceramic people, but it's because of the high sintering energy use, it's not good. And so stone, as I told you, has no energy to create it, very low energy to mine and extract and process it. Being locally available, the transport routes are short, it can be 100% recycled, and as it's so durable, and that's very important, it lasts for centuries. You have excellent thermal mass, very low U value, and therefore there is no need to replace the facade as it's very well maintained and durable, which is why great architecture over the centuries that is actually still with us today is made from natural stone. And you may say, well, this is yesterday's news, but let's look at some contemporary architecture in New York City. Hudson Yards, built 10 years ago. This would have been probably designed today with a lot more opaque material in it than it already was, but it was obviously designed from a decade ago before the carbon pressures came up. This is a tower here from Tishman Speyer. You know, glass is obviously not going to go away because we need the lighting. But you know, just planting a few balconies with some planters doesn't make it a low embodied carbon facade. And as we compare this, the embodied carbon of the same exact U value dramatically decreases based on the choice of your opaque facade material, which there is still a window-wall ratio that involves glass. So there is some phenomenal buildings built out of natural stone in contemporary architecture. We heard Joshua Ramus before, who was building the Perelman Center next door that he didn't mention, is also featuring natural stone. But these are all buildings around the world from top-notch architects, one of them I'm going to show you later, which are featuring natural stone very intentionally, and they are super low embodied carbon, which is the key feature. How are these facades built? There's many ways to build or unitize a stone facade, ranging from the hand setting to bracket rail systems to even dimensional pieces that look like precast, all the way to unitized systems that involve precast, UHPC, or unitized curtain wall. But let's look at the carbon footprint, embodied carbon footprint of those. And I've even added honeycomb here, which we categorically don't use because it delaminates, and it's just a matter of when and not if. But it starts at 7 kilograms, and I apologize, this is in square meters, but divided by 5, and then you get to the square feet in pounds. It ranges from 7 to 350 for the exact same fascia, just having a different substrate system that carries that. And we've done the same analysis for brick that goes from handset to GRC brick, UHPC brick-faced precast to unitized, where there is very dramatic differences in the embodied carbon. And you should all be aware of this when you specify these systems. Then over to terracotta that comes in many facets, precast, UHPC, which can actually be used as full curtain wall elements featuring brick or stone on it, GRC, metal panel to steel glass and pure glass facades. So now we have put some time and research into this, and we have created a matrix to combine all these fascia materials with facade systems, at least the common ones that are available. We looked at for a typical thickness, natural stone in New York it's 50 mil, but we only calculated it with 40, it doesn't make a big difference. Precast, 6 inches, and we now calculated painstakingly the weight of every component of these systems, put this in a giant matrix, and expressed it here as a chart. So what you see is basically what we will call an index, where you have a very clear differentiation of material, facade material and facade system. And you can see, just to give you one example, we have like a UHPC panel with stone on it. It has 74, and this is kilograms of CO2 per square meter, okay, not per kilogram material, because it is relevant how thick you apply it. It goes all the way to 500 kilograms of a metal panel facade on a unitized curtain wall. So that's how dramatic those systems differentiate. And if you express this for a 100,000 square foot facade, this is now in tons, it becomes very measurable. And think about all the balloons that kind of dwarf our cities that are piling up. So now, from the theory, let me show some examples to you where we've already done this. That's why I said it's already available today, these solutions. It's not something we need to still develop or research on or do tomorrow. We can do this today. And we had a project that we executed in Frankfurt, which was really looking at some architecture in London, where the architect initially wanted to use precast, but then decided to use a limestone because of the carbon footprint. So these are full floor height limestone elements that are shaped, that are cut out of blocks very efficiently with minimal waste. But you see the carbon footprint of these two facades, you have a 63% carbon footprint reduction. And this is some of the details here. With a 4-point aluminum anchor system, drainage behind. You can see the solid pieces over here. And then the installation is much like precast, with a auto crane, and super quick and efficient. And it's been so well received, this building, that it has found many repeats in Germany. People are actually copying this building, and they are now emulating it with other natural stone applications, different types of stone. So, success story. Here's a Tishman Speyer project in Frankfurt. It's the Opera Tower, where there was an in-depth study done by the German Stone Association, because initially it wasn't clear if this building was going to be all glass or partially glass and stone, which was finally chosen. And you can see here now, this is an all-glass facade, which is still about 10% opaque, to be precise, but we have about 250 kilograms of embodied carbon per square meter. The building that was realized had 33% handset, 17% unitized stone, and there was still 50% glass. But we got 40% carbon reduction from taking this route. And what I want to point out here, because the study also went into the operational phase, so this was a whole life study, the maintenance phase, and this was driven by the better U value of the glass then. This was 10 years ago, where the glass wasn't as efficient. It is 3 times the savings on carbon if you take in the operational phase, because there is so much heat gain and heat loss that has to occur with the glass compared to the stone area, that this cost actually the building to have 45 million euros, which is about $50 million US in energy savings on over a 50-year life cycle. Heating, cooling, ventilation, and was the savings. And then it's not just about the global warming potential of these facades. You also have to look about acidification, ozone depletion, and other features, that are very relevant for urban environments, that are drastically different between those two types. So this building was later repeated in another stone building by Tishman Speyer in the same town, which, this could be a metal facade or it could be a precast, but no, they chose a white limestone very deliberately, having learned from this prior experience. So there's another building that's going up in London right now, with Make, also a huge structure. It will actually be the largest and tallest stone building in the city of London. And the architect was playing with the materiality. He was loving titanium, double fire, terracotta, which you remember has about 5 times the carbon of stone. And due to that reason, he ended up using a lion's share in limestone. But had the whole building built in terracotta, it would have been 900 tons of carbon versus 130 that the final building actually has. And then, you know, a lot of products mimic others. Precast can be made look with forms and form liners like brick. Stone can actually look like terracotta. This is the Hyatt Hotel at Potsdamer Platz. This is the Alliance headquarters in Frankfurt. So look at this drastic difference in embodied carbon. You can achieve the exact same look in stone. You take a red sandstone, you mill in these longoton or alphaton long thin baguettes, and you can achieve that look with a much lower carbon footprint. And even for way more window-oriented facades, stone can be super efficiently unitized on thin precast or ultra-high performance concrete, and then crane set on site to prefabricate it more. Same goes for brick. This is for a famous German architect in Frankfurt. This is actually not a brick facade, it's a stone facade. The stone pattern is milled into the panels, which has one huge benefit besides the lower carbon footprint. By milling faux joints into these panels, you can set a much larger, this is a handset facade, a much larger panel area in a shorter time because you no longer have to layer the bricks. But as we understand that architecture needs to speak many languages, we have actually developed our own brick line now, where we recycle all the stone sludge that comes from milling the blocks, and we can add between 30 and 60% to brick. And we have a green brick that's partially made out of stone powder. This is a project also worth mentioning in London, where KPF wants to use the existing building, that's the old British Telecom building, as a quarry. So they said, oh, we have all this beautiful Portland stone, 75 mil thick, let's use that. Let's take it down, cut it down, and reuse it. And so in this approach, we have been tasked to compare a stone face precast facade that's, in this case, 8 inches thick, yeah, 8 inches thick, and a half thickness UHPC limestone facade, only in total 4 inches thick, 10 centimeters. And we have calculated the carbon, even including the transportation costs, and we came, and both materials can have recycled content. We came here to a 38% carbon reduction on an almost 80,000 square foot facade. The transport alone is worth mentioning. You go from 18 to 9 tons of carbon just by being able to ship the same amount of panels on half the amount of trucks, which is much less emissions and wear on the road. And so therefore I want to really quickly leave this with you. This novel system sits really as a new category in between stone face precast, which is heavy, has a pretty poor carbon footprint, always requires a tower crane, which is often a scarcity factor, and you lose a lot of floor space. But we have this novel system that is mechanical connected, so there is thermal separation, no risk of delamination, and which can be done at a much lower carbon footprint. Just here some examples, and we can do some really exotic shapes and sizes with perforations with it, even entire unitized curtain wall elements where the glass can be pre-installed. Or, as in this building in London, where the facade was converted from precast to UHPC, and a sixth floor could be added without changing the superstructure or foundations, just by reducing the weight of the facade by 150 tons, going from precast to UHPC. So I want to close with this project in New York, which is with Studio Gang. Jeannie Gang is a big concrete architect. She has built a lot of famous concrete buildings. But this is the Natural History Museum, so a natural material was chosen, and it couldn't be a more complex facade. Almost 5,000 pieces of stone, each bespoke. None resembles the other. So it is a very good example of an innovative Revit Rhino designed modern facade design where people would say, you could never build this in stone. Oh yes, we absolutely can. And look at some of these sections here. These are modeled, then done with a 5-ax CNC machine down to 1 millimeter tolerance. We use point cloud scanning to ensure dimensional accuracy, and there could not be more variation in this. Hook stones, soffit stone, crease stones with some back carving, really nice, and the production is fairly complex, but thanks to modern CNC technology, we can do this in a few hours in our facility. And now you'll ask me, how do you unitize this? Well, there was a lot of different options we looked at. This was never done before in this complexity. So these were the options available. One of them was finally chosen, but it ranges from a steel frame back system called strong back system over stone face precast all the way to UHPC that could have carried it at a much lower thickness down to dimensional stone. The steel frame was chosen just out of the lack of other bidders to do this, but this is what some of the assemblies look like. Certainly not the lowest carbon footprint on the steel, but the result is going to be striking. And I want to close by also mentioning there is stone that can be used for load-bearing facades and walls, as Amin Taha has already used in London. He built an entire exoskeleton out of limestone that comes directly from the quarry, and the carbon savings are gigantic. See, the steel girders are directly tying into the stone blocks, and we're working on a job in Frankfurt right now with a famous German architect where we're building the entire exoskeleton out of structural stone. So please keep in mind, natural stone is an excellent way that's already there today. Has the lowest embodied carbon footprint of any material available, can emulate the look of other materials like brick and terracotta. It's highly durable, and that's really important because that means it will last long and you don't have to replace it early. And UHPC is a great alternative to unitized facades other than aluminum and concrete, and you can use stone structurally. So thank you very much today. It was a pleasure. Thank you.
Thank you very much, Philipp. Thank you for ruining the day for all the glass and aluminum people here. So repositioning buildings is something that will be more and more the topic of the day in the post-pandemic world. We are seeing that workforce is changing. People like to work from home. We have a big, huge inventory of buildings that are used currently as offices that we have a questionable use for them. So our next speaker is Lauren Schmidt from KPF, and she will introduce to us, or reintroduce to us, the repositioning work that was done on 660 Fifth Avenue. Are we okay?
Yeah.
Okay. So Lauren, why don't you come up so everybody can see you. Thank you very much for taking the time doing this.
No problem.
It's highly appreciated while Ahad is going through the repositioning of his system to make this work.
Just give us a couple of minutes. This is a PDF, so we're just trying to convert.
Yeah, why don't you give a microphone to Lauren to speak a little bit about her practice?
I think, but no, just a sec. We're just trying to get a full screen. Otherwise, parts of it is cropped. So trying to solve that out. Just a second.
Well, one of the problems is Ahad is a perfectionist, so it has to be perfect for it to work.
Sorry? There's no Adobe in this, that's the problem. Otherwise it would have worked. It's opening up in a browser, so that's the... F11?
Here we are.
Okay, that was easy.
Thank you.
Thank you. I'm a Mac fan, so I do not use Windows.
So let's leave the stage to Lauren, okay?
Yeah.
Thank you. Thank you very much. I'm going to be following those very great talks with discussion about repositioning. And a quote that is known in the industry is the greenest building is the one that's already built. So I think repositioning offers a chance for us to take advantage of carbon that's already been put into the atmosphere and work with ideas of some of the built environment that we already live in today. So the project today I'm going to be talking about is 660 Fifth Avenue. And it's actually cutting it off a little bit, but hopefully we'll be fine. 660 Fifth Avenue is located on Fifth Avenue between 52nd and 53rd Street. This is a property that many of you have seen who are local to the city, and one that was built in the 1950s. The little bit of history about the facade of this building is it is a pressed aluminum and glass, one of the early unitized systems that was ahead of its time, and allowed for a great unitized construction, but also, of course, the environmental and thermal performance of a thin aluminum panel and a single pane glass has been much improved over the years. This is an image of the existing building, looking from the interior, so a shot of what the existing product was, and we'll talk a little bit more about where we've taken this so far. The building as designed, as I mentioned, was an early unitized system, and this is a still from a documentary done during the construction, and showed the ability to place these and install these unitized panels in a system of steel posts that were cantilevered off of the slab. I think one of the most important things with buildings of this time is taking a look at the steel moment frame system and the structure of the building. Here you can see from this still from that same video the 19-foot column dimension spacing, and then the 11-foot floor-to-floor that's typical throughout this building. Obviously, these metrics are a little bit substandard compared to the Class A office buildings that are on the market today, but again, we took this as a challenge in trying to find a way to make opportunity out of this. One of the other important aspects of a steel moment frame is you have a lot of members, but they're all equally supported, and it gives you a great flexibility for repositioning with the ability to open up double height spaces and not worry about single columns that are really supporting a large component of the building. So with that, we challenged ourselves to say, what can we do to improve this? Part of our scope was, of course, a full reclad as well as repositioning of the building. And working with Front on this, we took a look at starting to evaluate sort of the myriad of options that you typically look at. Looking first if your standard 4'9" to 5-foot module and what that would mean across the building, and then challenging ourselves with already having the density of this 19-foot column spacing, what we could do to further open up the facade because we were dealing with floor-to-floor heights that were a little bit less than what's expected for Class A offices. So with that, we began to push the boundaries and look at expanding what our module could be and taking it one step further and looking at expanding it to the full column bay. This was some of the initial early studies we had done and before we really knew what this meant, but we were given the opportunity to look into this and try to think about what we could potentially resolve from this. This is a drawing of the final mega panel that we have on the building right now. And one of the things that was really important for us is obviously supporting it with this steel moment frame connection. The actual individual members of the building are not as strong as you would expect in typical construction these days. And the slab, which is typically what's supporting the facade in current facade buildings, is not as strong as you'd like it. This is really a 4-inch facade and draped between very closely spaced beams. And so the challenge was, how can we resolve the size of this panel? And we were able to do that with configuration of the shadow box, which you can see here is a 4-sided shadow box with the joints centered actually within that opaque zone at the slab, both horizontally and vertically at the columns. And this starts to hint at some of the complexities of this shadow box profile that we created, which we'll get into a little bit more. And a lot of these decisions, which seemed a little bit arbitrary at the time, really coalesced and became the characteristics that solved very technical challenges while allowing us to produce something that we felt was really true to the design of the building and what we were trying to achieve. So once we had an initial sort of go-ahead to take a look at what this would mean with this mega panel, we started to dig into some of the details of what we'd need to resolve in order to get everyone on the same page and make this possible. One of the first was, of course, what's commercially available for glass. You can see here a standard glass size is the 10'6" dimension by 19'8". This is a pretty standard glass size that's fabricated. The facilities that were mostly automated use this glass size for all of their production, tempering, coatings, etc. And so this is sort of the base material that you're working with. In a typical standard 5-foot or 4'9" module, you're taking that large piece of glass and cutting it to size for these IGUs that you're making. However, if we tip this on its side and looked at it at the larger panel, we realized that we could actually try to make the most use out of this large production that's being made and really limit ourselves to trimming this standard panel on one dimension and maximizing that 3.2 meter by 6 meter module that's coming out straight from the fabricators. And this was something we used that 10'6" module in all of our detailing to help minimize the amount of waste and help to speed up the amount of fabrication that would be possible. Interpaint told us during these productions that was who we ended up using on this project, but we were able to talk to multiple fabricators who were capable of doing this. But Interpaint told us they could produce 40,000 square feet of IGU per day at this size because this is exactly what they almost were coming straight out of the ovens. And that allowed us to produce panels for an entire building in a little over a week. So it's something that they were really comfortable with, and there seemed to be an understanding that it wouldn't actually be more expensive to produce a larger panel. In the end, it's actually going to be easier for them because of the reduced amount of waste as well as the minimization of handling and cutting that needed to be done. So we went and did a lot of visual inspections, looking at full-size IGUs from multiple fabricators, obviously concerned about the visual quality as well as their ability to create panels at this size and meet the deflection criteria and other aspects from a performance standpoint. And looking at these, we were able to narrow down and really think about also the balance between the thickness of the lights to reduce the amount of pillowing effect, but also making sure that the visibility of roller waves, which are usually increased in the thicker lights, was going to be as best it could be for this project. This is the final glass IGU buildup that we ended up with the project, with the outer light being a 8mm laminated and interior 8mm as well, and working with the fabricators to confirm that this would meet all the requirements of deflection because we're looking at something that's spanning that full 19-foot column spacing. Looking at this from the exterior, this is a rendering, and this was one of the initial images that we produced once we got a buy-in of this idea that we weren't totally crazy. And from here, we were able to dig into some of the details of how we could actually get this fabricated and detailed. You can see it here spread across the facades of the building. The massing of this building really remains unchanged. And we took advantage of the fact of these terraced setbacks that were classic to these buildings in this time to allow for terracing, etc., across the building floor plates. Digging into a little bit further, this is an image of one of the first panels that we set on the job, immediately adjacent to the existing facade. This was just for a mock-up that was done, so not the exact final detailing, but what we needed to figure out was how to support these panels. And so we were able to work with the existing structure here, you can see from a view from the interior during installation, using the existing columns and asking this panel to actually span itself from column to column rather than relying on intermediate supports. And through a lot of analysis and cost analysis between this large panel versus even half size or a quarter size, we found that it was actually most efficient structurally to have the panel itself span between these columns. And that would allow for minimal attachments to the existing building structure, and also putting the load where it actually was able to be received, as the slab was really not able to carry any load. The picture inset here is showing one of the attachment angles off of the back of the panel in production. And so, in reality, a rather simple solution that was achieved through a very long and detailed set of explorations. Zooming into the details of what this panel is, again, we had looked at this four-sided shadow box, initially driven by both design and technical aspirations. And the final panel is a combination of a steel structure as well as aluminum. You see some of the traditional aluminum extrusions, etc., but also this steel support that's sort of hidden within this tapered, scalloped shadow box, which allows for this frame to exist. And working with Island exterior fabricators, we worked through the detail of this to optimize not only the design intent, but also obviously structural ability to span and to attach back to the panel, the columns, and also support the dead load of these large lights of glass, which was a concern, of course. And so here's a rendered image of what that intersection looks like from the exterior. Working with these large modules, we wanted to make sure that there was an articulation and ability to see this change over time as the sun angles change. So having that nice, that slightly canted shadow box really allows us to be a dynamic facade when you look into the details of it, as well as provide the space and necessity requirements for code, structural support, etc. All of this, of course, was while balancing what the interior was going to provide. Obviously, the importance of this is, in a spec office building, is creating a space where people want to be. This was really the image that sold this idea from the beginning. Obviously, the exterior views were beautiful, but looking at this and what you could offer from that original image of what the building had, you could really have this beautiful, breathtaking, clear expanse of glass. And we sort of mimicked that idea of this angled frame on the interior to help mitigate the fact that we were dealing with the lower floor-to-floor heights and the tighter column spacing at the perimeter. Getting into a little bit on the details of this project is currently under construction, very far along as far as the panel fabrication is concerned, but this is a quick shot from Island of their fabrication facility and their ability to also figure out ways to optimize the fabrication and think about how this glass would be installed, and also obviously meeting the details of schedule. This is the first panel off the line. You can see here for inspection. And then one of the first panels installed on site. And one of the beautiful things here is that the panel really starts to disappear, right? You walk into this space and you're actually wonder to yourself, where is the facade, right? You just see these columns. So that was something that we felt that, we had actually, we're really happy that we had achieved this. And then also an important aspect is logistics from a construction standpoint. And this was something that Brookfield and the construction team, Turner and Island, spent a lot of time on to justify the ability to do this. One of the things with repositioning projects is you have the benefit that the superstructure is already there. Typically the tower crane is always, the superstructure gets prioritized, and therefore you don't have the ability to use it for installation. Here, because we're using the existing structure, we were able to make use of the tower crane primarily for the facade installation. And these panels are delivered on site and lifted directly from the truck onto the facade, so it limits the handling time. A side note, the slabs couldn't even support resting these panels temporarily, so that was a benefit as well. But from there, the installation process is quite fast, and nobody really knew exactly what the time difference would be compared to the typical 5-foot module, but installing one of these larger 19-foot panels doesn't take that much longer than a 5-foot. So you're really seeing a savings with regards to time of installation, which was a great benefit, and then became another opportunity cost here to allow us to push the envelope with this mega panel. These are some views of the construction underway. As you can see, the existing facade starting to be peeled away, and the new facade coming up from below. And into some of the details, shots of the construction. And one of the most important things, of course, when you're working on these repositioning projects is understanding what you're trying to achieve, not just from the exterior as the architect, but really for the building user. And what we're offering here is an opportunity to see the potential in a project, in a building that exists here on the market in New York City, but maybe is overlooked as something that's less desirable. But by pushing the envelope from a fabrication, materiality standpoint, and construction and logistics, we're able to achieve something that brings a whole new breath of fresh air to this building and makes people see it in a completely different light than they're used to. And it also, of course, benefits of reusing existing buildings and the repositioning process in and of itself. And with that, thank you.
Thank you very much, Lauren. That was very, very interesting. Appreciate that. So next is my dear friend, Eric Verboen, if I may call you Eric, to come up here. Okay. So he will be, together with his panel, talking to us about the local law 97, which was touched upon several times already today. So they are setting the stage, and I want to actually let Eric introduce his panel himself. As he's getting wired up.
Go. Plus moderator, yeah. 6. Want to ask him to stand or what? Hello. Turn the mic on.
So looks like this will be Eric's chair.
Yeah, so we'll have 6 and just go. Can I have the mic on, please? Can I have the mic on? Hello? Hello? Yeah. So, I'd like to thank again our event partners. They've been extremely supportive in helping us organizing this event. All of them have their booths outside. I urge you to please visit their booths during the networking breaks or during the end of the event. Meet and greet with them. That's what they've paid up for, to meet you all in person. So please do meet our event partners. We are not giving a goodie bag this year. Instead, we have a USB stick which is across your lanyards. So all their brochure soft copies have been loaded onto your pen drive. I don't think so many people know there's a pen drive stuck on your lanyard. This was a feedback from other events. So no more printing brochures. So we have all their soft copies on your pen drive on your lanyard. So over to you, Eric. You can introduce your panelists.
Thank you very much.
You need you want to sit and you can click your slide.
I'm going to start with standing.
Okay, cool.
All right. All right. A little delayed, but thank you guys for your patience. My name is Eric Verboen. I am the National Director of Enclosure Engineering for Walsh P. Moore International Engineering Company. I want to also mention that we are the sponsors of the reception later on. We are always a fan of sponsoring cocktails, so please enjoy that and join us for that. And I also like to start with thanking Zak for selecting such an interesting topic, and one that I think a lot of us in this room are probably heavily involved with, whether we like it or not. And having myself and these panelists to join us in speaking about it. So this is the first panel, panel discussion in the event. So really happy to do that. So the topic today is Local 97, which is the cornerstone of the Climate Mobilization Act of 2019. And I'm sure the New Yorkers in the room are all too familiar with this. So we won't get into the nuances of the law insofar as to say, as Attila mentioned earlier, that it's the largest climate solution ever put forward by any city in the world and is designed to dramatically decrease carbon in New York City. So it was enacted in 2019, and we've had a few years now where this was the elephant in the room, something that was most owners and designers and professionals did not try to ignore, but continued. The program continued to push forward, whether we liked it or not. With the goal of reducing carbon emissions by of buildings 25,000 square feet or greater starting in 2024 is no longer the elephant in the room, but actually the monster under our bed. My company is involved in a number of projects that are targeting, meeting the local 97 requirements, but it's astonishing the number of projects that we are involved with that are doing facade retrofits where this isn't even on the radar of the owners. So it's something that we need to be keenly aware of and educate our clients and owners of what's coming. Because to 2024, as we all understand how long it takes to design and implement significant changes in your building, especially the facade, is right around the corner, and it is the monster under our bed. So with buildings contributing to 70% of New York City's greenhouse gas emissions in the city, the environment in our industry has, you can see the immense sort of kind of impact it has in our industry right here. This 50,000 buildings within the city itself it has 25,000 square feet or greater. So we're going to be busy getting this pulled through. And there's a lot of help. We have a lot of help, and we'll talk to some of the people on the panel who are helping us in that process. But the process and the rules of engagement and the metrics have changed considerably. Where good design and satisfactory implementation or execution and happy end users have historically been the goals, compliance will now mean something completely new. The new metric is accountability, and the intent, where intent is validated through testing and reporting is mandated and reviewed. So what we see here is, accountability, performance is actually the metric, not just good ideas, good energy models. It actually has to be implemented well. So these are very exciting times. Maybe many people may think, and especially owners may think this is scary, but it's an opportunity for us as design professionals, as builders, to really set the bar high for the rest of the world and meet these aspirational goals. And as such, we've assembled a panel today that consists of individuals that define, set policy, and assist owners in navigating the process. We have a team of designers that either focus on repositioning or integrated solutions, or even next generation solutions to enclosure systems. And then we have someone who is very astute in developing new ways of testing and validating the concepts that we design. So I'm going to introduce them by letting them introduce themselves through a number of their own slides that they had provided us. So we'll start with Elizabeth.
Thank you. There's an on switch for all of you. My name is Elizabeth Kelly. I am the Senior Deputy Director, just had a title change. Associate Deputy Director of Strategic Initiatives at the New York City Mayor's Office of Climate and Sustainability. Work just around the corner downtown here in Lower Manhattan. Curious to know how many people feel like they might be able to give a presentation on Local Law 97? Okay. How many have heard a presentation on Local Law 97? Okay, and then hands down, who's not from the New York metro area? Okay, just trying to gauge this. So through my office, we work on developing policy and programs to support New York City's rapid decarbonization with a goal of carbon neutrality by 2050. And as part of that strategy, we are advancing policy and programs to reduce carbon emissions, specifically in the building sector, but also through waste and transportation and energy distribution. In 2019, New York City Council passed the Climate Mobilization Act, which is a suite of legislation that with the goal and intention and drive to rapidly reduce carbon emissions throughout the built environment, and that include Local Law 97, as Eric mentioned. I really liked your slides. I can't use those kinds of slides. I have a boring slide. But it hits on some of the high points of Local Law 97, being that this is a law that applies to all buildings over 25,000 square feet. There is a carbon emission or a GHG emission cap that is applied to all buildings based off of their occupancy typology. So a multifamily building has a different coefficient target than a hospital or a hotel. These emission caps come into effect starting in 2024. So we expect about 20% of the buildings covered by Local Law 97, 20% of the buildings covered by Local Law 97 will need to take on some pretty extensive work to meet the budget by the 2024 rollout, with another about 70% of buildings needing to take action by 2030, which is the next year that the budget really kicks in. In order to comply, you'll need to have a letter signed by an architect or an engineer that certifies the building's square footage, which can sometimes be complicated. That'll take some time. And also to verify that the emissions are below the cap. There's plenty of tools out there online. You can go to nyc.gov/accelerator to find a tool. It's a calculator. You put in a property address or other building identification, and it'll show what that property has in terms of emissions, and then what their penalties might be for 2024 and 2030. Lots more to talk about, but that's our quick introduction.
Thank you. Kate?
That's me. Hi, I'm Kate Boysh. I'm an associate partner at Paycom Freedom Partners. I'm showing 1271 Avenue of the Americas, which I know Marcus spoke about earlier. It was designed in 2014 before Local Law 97 and before the new energy code. But for us, I'm showing it because it's really a catalyst to our involvement in a lot more repositioning and renovation projects. And what's important as an architect, finding our place in all that, I think, and finding where we can use Local Law 97 is really leveraging and expanding our multidisciplinary team so that we can address carbon as well as all these other things that we want to do with a building, and really find the sweet spot in there where it's going to be commercially viable to retrofit and renovate and reclad.
Thank you. John?
Hi, everyone. So a little bit different, coming at it from the engineering side. I'm John Colatrella, Howard Zimmerman Architects and Engineers, a firm that was founded on doing facade safety work. And now, as we come into the Local Law 97 world, and head of our engineering department, specifically on the MEP side, integrating all of this, you know, working on the facade aspect of it to try to get the most performance and efficiency out of it really sets up our engineering department to take advantage of that. And we're really looking at it from both sides of the coin, because all the milestones that need to be met are not going to be achieved by either, you know, the facade only or the MEP systems only, and it's really going to integrate both of them to get to these milestones. And as pointed out previously, a lot of our clients they're very, very concerned about it. You know, 80%, I would say, of our clients are probably going to meet the 2024 goal right now, but 2030, you know, most, if not all, are not going to meet it without doing substantial work. And as we've been talking about all today, there's a lot of planning. There's a lot of calculations, modeling that needs to take place to get there. And it really is an integration of both. And you know, our office is trying to bring that all together under one roof, to analyze it all together, come up with a plan, implement it, and take advantage on the engineering side of the improvements on the facade efficiency.
Thank you, John. Jason?
Okay. So, hi, thank you, Eric. Great to be here. I'm Jason Boland, Senior Vice President at ACOM, where I direct for my division Research, Development, and Innovation in an initiative called iLab. Local Law 97, to me, I'm on the Grid Working Committee, so it's as an architect, that's quite an education. It's a really messy piece of legislation, and I say that with great love, because all legislation is messy. If you think there's an orderly transition to electrification, you're mistaken. It is going to be a messy transition. What I really like about this, and why I say with great love, and I probably stand for this, is that, you know, the benefit of pushing to deep energy retrofit work with the facade allows us to rethink the mechanical systems at the same time. And if you've been tracking this, it's at least a $70 billion industry in the US in the next 10 years. So it's an enormous market from a productivity perspective. What I like about it is it starts on the way to setting targets that we can't currently meet with the way we build buildings today. So what I want to do is take all of this junk, even though it might be smaller junk and higher technical junk that helps us with the thermal comfort, and stick as much of that into the facade itself, so that the mechanical system and the facade are actually the same system, because that's where the majority of our load is. And that becomes important towards electrification, because when we can deal with the operational carbon in a much more efficient way, and as the grid cleans up over the next 30 years, we're going to be left with embodied carbon only. And we'll be focusing on that in another round. But in order to get there, we still need to get to electrification.
Thank you, Jason. And finally, Elliot.
Hi, everyone. My name is Elliot Benor, and I run building envelope testing. We're a local testing lab, and we concentrate on quality control of building envelopes. And lately, over the last 3 years, we've been transitioning to measuring and quantifying energy loss and gain through the building envelope. I was on the New York City Energy the Energy Code Revision Committee, and during that process, they snuck Local 097 in on us. We were surprised that it actually passed when it did, but pleasantly surprised. And I knew then, I guess that was 2018, that this was serious and that we all needed to pull together to develop more tools that we can present to the AEC industry to be able to make more effective decisions about what they do. We're big believers in modeling. I think for new construction, energy modeling is the way to go. You can't build a building today without all the modeling software that everyone's talked about today. But on existing buildings, that becomes very, very challenging. So our focus was to develop a system to be able to quantify the energy loss through the major factors, air leakage, U value and R value, and we've been working on that steadily since and hope to have it ready to go for Local 097's retrofit work. The key is working together, working as a team, and that's what I think we have here is a great team of people. We represent the type of teams that need to be on all of the projects.
Great. Thanks, Elliot. I'm going to go back to Elizabeth, your slide, just so everybody can see the sort of, and I'm going to take a seat as well. So we can ask some questions and have a discussion. All right, we're going to start with a little bit to do with the sort of investment side of things. We all know that there's a considerable financial investment that's made by owners in order to do deep energy retrofits, or maybe not so deep, just to comply for 2024. What are some of the ways that the city or design is able to offset the costs associated with these energy retrofits?
Well, one thing that I didn't mention that's a really big bullet point on my slide here is that buildings that don't meet their budget are fined. And so putting money, like a price on carbon emission changes the economics for buildings. Because before it was all about savings on utility costs, demand charges, but now you're also looking at a $268 per metric ton fine, which, you know, makes a different type of investment decision possible. Another thing worth mentioning is just this year, May 2021, the city launched commercial property assessed clean energy financing, or PACE financing, for commercial buildings, and commercial is inclusive of multifamily, commercial, institutional, industrial, just not residential buildings. And we've already closed about over $100 million in loans and that's available for retrofits, and people are using that as a really a less expensive option to mezzanine financing, and a lot of traction there. We actually have a webinar on the December 1st specifically designed for engineers and architects to learn more about the technical requirements of that program.
Can I answer that from the other perspective, which
Absolutely.
is working for a developer, let's say, right? So for us, what is really important is being able to see holistically how the building is going to respond to whatever retrofits we're doing. So not only in terms of what an owner would save by not getting fined, but how that affects lease rates on the building, internal users and their satisfaction with the building and its popularity. And what's really exciting to me is, so Local Law 97 is a stick, but there's a lot of carrots too. And it's exciting to bring all those people together to be able to estimate what that savings is going to be or what that gain is going to be, and we're still working through how to do that, and then come up with a better product where we don't tear buildings down.
Unless somebody else to follow up, I can.
So there are some incentives right now from the local utility companies. Actually, all the utilities in New York State have programs for the commercial and industrial financing of projects like this. And they're not loans, they're actually grants that they give you. You have to prove certain milestones and metrics, but there's considerable money that everyone's been paying in their electric bill for the last 50 years that's been accumulating for these programs. So I encourage everyone to look into the Con Ed and National Grid C&I programs.
So, you know, that was, we were talking a lot about the sort of the hard costs associated with these deep energy retrofits, but there's also some other costs associated with the disruption that it causes with tenants, right? So, Kate and John, maybe you can speak to, what do you do to educate your clients on, the process of deciding which interventions are done that might cause less disruption and continue leases from.
Right. I think that this really comes down to a lot of planning ahead. I'm talking years in advance. There's a lot of retrofit projects on the engineering side that take us years to implement in phases. It could be plant-based work. It could be, parallel infrastructure to then phase into the new equipment. There's going to be taking advantage, in shoulder seasons when heating or cooling, that 6 to 8 week window is very critical, in our world to get a new piping system or a new plant swung over. It's just a lot of planning. It really comes down to a lot of planning and getting ahead of this very early and understanding what's going to be entailed.
One thing we're looking at now in particular is about overcladding versus recladding, and how much can you do just from the outside, and how much can you do just from the inside, and how can you marry those things with a leasing program that the owner already has, right? So maybe they'll have empty floors at a certain time, but involving everyone in that discussion early, the leasing people as well as the logistics, and has been helpful.
Right, and I think. John, you started getting into the integration piece, right? And so, obviously, this conference is about facades, but facades are only part of the puzzle in regards to Local 197 and having buildings that perform to those standards. So, maybe some of you can speak to how critical it is to look at in an integrated fashion at Jeep retrofits, and how do you educate your clients into the most efficient ways to do so? I think there's some naive thoughts out there, not poorly intentioned, but like that they can just replace the windows, or that they can add some more insulation, right? But that might not get them there. So how do you respond to that?
Pretty simply. It's a holistic approach that it's going to take. Otherwise, buildings are going to be faced with major fines. I think everyone up here realizes that and conveys that on a daily basis to our clients. With that being said, I don't know. It just. I'll start by saying that New York City, for anyone who's not familiar with it, there's a lot of systems that are just so old. A building still using oil, still using steam distribution, right, to heat their buildings, and these deep retrofits have to go beyond, again, just a window replacement or a window inside of a window, which will definitely get you somewhere. Will take advantage of some Con Edison rebates, and these plant upgrades, it's more than just getting a more efficient heating plant or a more efficient chiller plant. We're talking full distribution change, going from, a steam building to at least a, hot water heated building where we can use setbacks and change the circulation temperature to, combat with the outside temperature, and not bringing steam up to 212 degrees to heat the building. So these deep retrofits, it's very eye-opening, and it's a tough conversation to have with our clients, because they think that they're just going to be able to get away with what they've always gotten away with, which is a small upgrade, and that's going to solve the problem. And when we show them the analysis just on the fine side, it's staggering, and when they see what these numbers look like on an annual basis, that's where the realization starts, and we as a firm start with that, what I'll call benchmarking, just to lay it all out there, what this looks like. Then at least we have their attention, because when you start talking about these deep retrofits, with a developer type client or somebody that is just very cost conscious, you're not going to get very far if you don't show those fine numbers.
What I think is, with electrification going to happen, the threat of a fine is important, but really it's the opportunity that it unlocks. So if you're going to own the asset for any length of time, you can get out ahead of that and push to electrification now and use this as a springboard, use the PACE financing, which is really important, use the other programs, use the increased value of the tenancies, all of those pieces together with an economic analysis, plus in 30 years, what do you want your building to be? I think makes a compelling argument about why you would look to do that now, and why you go through the trouble of bringing engineering and construction in at very early stages to make those long-range plans about how to keep, for example, the building occupied as much as possible, because that's an offset revenue stream that's really important. If you have to empty the whole building out, you have a very difficult time convincing a current owner-operator. I imagine that we've been through that here on the stage. But if you're able to say, I can keep it 50% occupied, 30% occupied, but if you could do it really well and be 80% occupied and do it in a measured way, you can offset a significant amount of that lost revenue. So a dynamic economic model as part of the engineering model, I think, is equally as valuable in what we're doing to tell our clients why you need to be looking at this type of more in-depth retrofitting.
So I think what's important to convey to owners is to start looking at your team as partners and not looking at this as a project by project task that you're going to take on in the building, because this is truly the essence of master planning. People, especially with bigger buildings, can't look at single projects or single parts of the overall building and say, I'm going to do what John was saying. I'm going to do the plant replacement. I'm going to do the window replacement. It really is a master plan, and some of the things have to be done in sequence. It's very, very important to look at the sequencing of what you're doing. The envelope should usually go first, but not always, and doing it in conjunction with a master planning entity, whether it's your architect, your engineer, some independent consultant. That's the key, because there is no getting around this on your own or with people working in silos.
And just to kind of add to that, I mean, if the facade does come first, which many times it does, I mean, that allows somebody like me to really take advantage in equipment sizing. That allows me to downsize plants, downsize piping, downsize pumping requirements. Even with the whole electrification, we need to do an electric service and distribution upgrade for the building just because it's antiquated. But it allows us to maybe have the same amount of power coming into the building and just, update it for, new code compliance. So there's a lot of advantage to be taken by going through that facade exercise, getting that as tight and as efficient as possible with testing, and then really take advantage of the upfront cost for downsizing the plant, and then obviously the operational savings.
So, Elizabeth, you mentioned the fines, right, and that being a potential incentive, right, for getting owners to rethink their building. And Elliot, you're talking about a whole team involvement, right? I'm curious, in a world where a poorly, or let's say maybe a well-intentioned design that was poorly executed potentially, or a poor design that was well executed, where does the sort of risk spectrum shift? How does that shift when buildings that are built or retrofitted don't perform according to what was estimated? Because the fingers get pointed, right? We can no longer hide, what the performance is, because we have to report it every year.
So I think the key thing from the new construction side today, because the minute a building is completed and occupied, it becomes an existing building and it's subject to Local Law 97. So I think another key message to get to owners is you can't play the same games you've been playing through the construction process. If you model, and the models need to be conservative because the DOE2 software engine that almost all the programs we use are based on is old and it's static and it's not a very comprehensive, although it looks extremely comprehensive, it's not up to the task of what we're asking it to do. So I urge everyone, always be conservative on the modeling. And then do not allow substitutions you do not understand. Because if somebody goes in during the value engineering stage, that always happens, and substitutes a process, a product, anything, it's going to affect the overall performance of the building in ways no one understands. Literally, we are trying to figure out how to do this as we speak. We've been developing a way of measuring the performance of an existing building, but there's not that much good information on low energy design buildings 4 and 5 years after they're commissioned. And what little is out there that's coming in right now from Europe is not encouraging as far as how the buildings perform post-occupancy. So we need to be conservative.
I think it brings into question, for 70 years, the architecture profession has been giving away responsibility to protect themselves from litigation. And you have to ask the question, after a fine, what's the next appropriate step? I think a fine is probably a great way to fund some other thing. That probably would be very useful. If you want to avoid a fine, then you can do something. With your, with your building and maybe get a better asset out of it over time. But the question to me is, who owns the performance? So the moment we're asked to turn the keys over but own the performance long term is going to create a major shift in the way we build buildings and who owns those components of buildings. Already energy systems are being looked at as taken off the books. So if you look at it from a cost to a state of good repair, then you have to get by legislative policy to a state of good repair, you'll start saying, maybe I don't want to own the energy system, or maybe I don't want to own the facade. What other parts do you not want to own as an owner that someone else will have to own? And that's an opportunity, right? To really clarify who owns the performance. So we talk about a state of good repair. In this case, it might be a state of good performance. And someone has to own that. And that's a potential for someone to find a business in that long term.
It's a good thing there's no table for me to bang my fist on, because this is where I get really excited. But, for us, it's trying to figure out how to model in order to, whether it's a new building or a retrofit, in order to really predict what's going to happen. And I don't think anyone's shy about being honest about it, but the issue is that engineers are kind of speaking one language and oversimplifying what the facade is doing. We're speaking another language and oversimplifying what the mechanical systems are doing, and that is not going to get us where we need to be.
There we go. There we go. Well, there was a few presentations earlier that focused a lot on carbon, right? And there was in the last presentation mentioned. An existing building is kind of the least impactful from a carbon perspective, right? So, Jason, you spoke a lot about you mentioned in your slides that there was this idea of integrating the system within the facade, right? And that has a lot to do with the people in this audience or the vendors outside that supply system and having them come together, right? From an embodied carbon perspective as well as a operational carbon perspective, how are we, in addition to sort of maybe finding solutions that are more integrated, what are we doing to be able to validate, as Elliot was getting to, like the their performance long-term after the initial, commissioning, but also be able to easily retrofit those retrofits in the future, so we're not having the same problem 20 years from now.
Yeah, I mean, I think it goes back to also who owns those parts. So if you never sell them, then and you design them for disassembly, and so you think of the facade as a mechanical system and you're going to change it out every 30 years instead of let it fail in 50. Or if a new technology comes on board, you can demount it, and disassembly for reuse is an approach that I think makes a great deal of sense. As well as I think if, we will likely see, because of the push towards these regulations where we don't have a technical pathway to get there yet, and you could see this out in California where they pushed they push energy efficiency way ahead of where the technology was. R&D caught up with that from a technology perspective and from a business model perspective in order to meet the regulations. Local Law 97 is a start in that same direction, where you have now room to maybe think about these things a little bit differently, and that the structure, if the structure on average is 120 years, you can let that sit, right? And if the facade has been 50 or 70 years, they're failing. We're going to see a lot more failures coming up in the next decade, but the mechanical systems, we don't think about that. All those moving parts, we're routinely moving them. And sometimes when we do tenancies, we do it even faster, like every 10 years. So the facade might be thought of a little bit more different, more temporary than we've thought about it in the past.
Interesting thought. Ellie, do you have anything to say about how we test, new methods of testing, new methods of analysis?
Yeah, so air leakage is huge in buildings. We've been doing blower door testing on houses. We haven't, but people have, especially in Europe, on houses to quantify air leakage. We understand R value and U value intrinsically. It's the flow of heat through our walls, but there are other things that we can't get a handle on. We're learning every day. The more we implement these measurement systems that we're coming up with, the more we're learning about what we don't know and that we're finding out now. It's more than just having two values for clear glass and spandrel glass and a third value for opaque walls. We actually have high heat sources in buildings. They're called human beings, radiators, mechanical equipment, and they generate heat at some specific locations in the building, like a radiator. We never considered that as facade designers before. We need to start considering that now, because what we're finding out is those spots on the building generate lots of heat to the outside, not just heat to the inside as they're supposed to. We never considered that in the past. We need to start looking at things like that. Mechanical system duct leakage is huge, especially on buildings like this. Commercial buildings, hospitality, we have high pressure ducts running multiple floors, they leak. Where they leak, you're losing lots and lots of energy. So there needs to be thought put into the maintenance of these systems and building them really better, and that's our focus, is getting people to build better when they build buildings.
Yeah, and continued maintenance, as we get better with the testing. On the consulting side, let's make no mistake, any client is going to be, can you guarantee these savings and these improvements and these fine reductions? And the more we can test and understand where we're at to start and where we need to go, I think the more comfortable we will be in terms of those quote-unquote guarantees.
Sure. Well, we're coming up on the end here, and I don't want to hold you for lunch, but Elizabeth, I'm going to put you on the spot and just ask, what is the city expecting 2024? Like, are you emptying out, making room in your vault for a bunch of fines, or are we gonna, or are we going to see a lot of compliance?
We definitely want your carbon, not your money. I think there will, our job right now, like, policy happens on a legislative process, but then you have to actually implement the policy, and that's what I spend my day-to-day doing. Outreach, marketing, technical assistance, training, workforce development, to make sure that this law is successful, not just for New York, but for municipalities and across the nation and across the world. We're so humble. And I really do think we'll get there. I think it's going to be messy, as we talked about, and we're really working out a lot of the kinks. Rulemaking is still happening. There's a lot of things that are unknown, but what we've talked about here, efficiency first, facades, these long-term investments that don't matter about the coefficient of the electric grid and a lot of uncertainties and crystal ball reading, but sticking to those basics of training, operations and maintenance, facades, of course, and just generally energy efficiency is going to be the path forward.
Great. Thank you all for joining this panel, and thank you for sticking around. Enjoy your lunch. Hope to see you at the cocktails. Oh, okay.
Turn the mic on, please. Thanks.
Do you want us to sit for the picture?
Yeah, there will be a picture. Thank you very much to this panel. That was really, really interesting and also important. I know we put you in a bad spot being between your presentation and the lunch, but it was very, very interesting. Thank you very much. For the group here, the session after lunch will be a breakout session, so there will be 3 partitions made. We do recommend that you take your stuff with you because there will be a whole new configuration. And then we will come back to the large session after the breakout sessions. Yeah, so we will have A here, B will be in the center, and C will be on my left, which will be your right. Thank you very much. Good job.
Can I have the photographer here? Can I have the photographer here? We'll take a photo opportunity with all the panelists. Yeah, photographer. Please. Got the photographer. Should we stand or sit? Stay on the stage. Attila, come, take a photo with them. Okay. I think, no, stand in front, I think. I suggest, yeah.
Taking my USB drive back. It was good.
Yeah, it was. It's hard. It follows the good one.
Yeah, definitely. Well, I mean, stuff like this is.
I'm Martin. Good job, Eric. Thank you.
1, 2, 3. Okay, they're in this room. They're the
2 o'clock.
2 o'clock, I guess.
PM scheduled. I don't
Yep.
know if it's reality.
Yep.
Thank you.
Yep.
It's the only part. It's the only.
Testing 1, 2, 1, 2, 3, 1, 2, 3, 4. Testing 1, 2 for room B. Terrence, can you give me some thumbs up that we're getting out of both speakers here? Testing 1, 2, 1, 2, 3. 1, 2, 3, 4. Testing 1, 2. 1, 2, 3. Both speakers, very good, thumbs up.
One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Testing, testing. 1, 2, 3, 4, 5.
So you should be getting me now. Hot coming through. Okay. That's you there. I can always turn this down a little bit to get it less hot on this microphone here as I'm coming in the room. That's better. Okay, very good. And I mean, yeah. And the Behringer, no one ever. I don't know who put the Behringer up to 10. I can bring it down. That needs to come down. Was it spiking the whole morning? No one really ever talked to me about Behringer, and like until like a minute before we went live. Yeah. Okay. Are both you guys here for the afternoon? Or that's right. In trying. Yeah. All right. So. But and you're just gotten your thing. No feed the camera, and okay.
This thing's doing video record. I hope somebody
Yeah.
hooked up some audio to it. Otherwise,
Yeah, that's what Ryan and I have been testing that all morning. That's been good.
Okay.
Ryan and I have I need to get your feed, and like I hooked him up from the next room. So, and then finally, 10 minutes before this, the Behringer needs a feed too. That's new information to me. Yeah. Yep. 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 Yep.
Testing, testing. 1, 2, 3. Testing, testing. 1, 2, 3. Testing, testing. 1, 2, 3. Testing, testing. We good? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Ladies and gentlemen, inside this room, I will be needing to make feedback noises. So there will be feedback noises for the next 5 or so minutes. Just so everybody's aware, I need to make them. So that's going to happen.
Hey, this is headworn number 1, sitting on my right ear, my downstage ear, which is probably the wrong ear, but it's still an ear, and I could probably pull this down so you don't lose all of that intelligibility from behind the face covering. I am interested in the world of facades, which is the thing that I can read in front of me right now. Not that I'm not interested in that, but I'm going to try to find something to read here. So there's actually a nutritionists and cookbook writers. Sorry, this is actually not quite. Coming out of this wedge. You have to adjust it from there? Okay. Say that again? Yeah, coming out of this wedge right here. Kill it? Yep, thank you. That's what's killing you right now with this feedback. That's what's killing you. I've got number 3 and number 4. Number 4 is on my tie, number 3 is on my head. Yep, understood. We've just, I think, fixed that, and I think that's going to clear this system up for you. Hey, 1, 2, here we go. Yes. It's coming out of the outlet, one of the... Yeah, the monitor. Check, 1, 2, 3. Yeah, take the mic off. Check, 1, 2, 3, 4, 5, 6. Let's get started. Check, 1, 2, 3, 4, 5, 6, 7,
7, 8, 9, 10. Check, check. 1, 2. All right. Check, check. 1, 2, 3, 4, 5, 6. Check, check. 1, 2. 1, 2, 3. 1, 2, 3, 4. Check, check. 1, 2. 1, 2, 3, 4, 5. Check, check, check. 1, 2, 1, 2. 1, 2, 3.
presenting the afternoon session. So for those of you who sat through the morning sessions, I thought it was really interesting that some of the most environmentally solutions really went back to nature. And I know no other office does this really well as the next presenter from COOKFOX, who really studied the building and studied the facade from a living environment and a living point of view. So with that, I'm going to introduce you to Spencer Lapp, associate at COOKFOX. He's going to be talking about eco-receptive architecture and the habitable facade, and hopefully a little bit about bees.
Hi, welcome. So my name is Spencer Lapp. I'm from COOKFOX Architects. I am also the beekeeper at COOKFOX. So today I wanted to walk you through a few different projects we worked on, and then kind of finish with a project that kind of was a way for us to experiment with some of these ideas, and not quite the same scale as a building, but really interesting. So the first project today, 250 West 57th Street. This is the COOKFOX office. When we moved into the space a few years ago, it gave us a chance to really reimagine what the workplace of the future could be. Our design practice is based in biophilia, basically bringing nature into the built environment. And you know, one of the core foundations to this is sort of a view shed, a way to you know, both be protected and you know, have a view out into the world. We also believe in, you know, communal spaces, but also allowing for you know, some smaller rooms, intimacy, and our office has a lot of the small rooms. Our office also has several terraces surrounding the office. You know, this gives people space to go out and relax, but it also creates ecosystems for you know, the natural world around us. And also on the terrace, you know, we have space for a garden. This is also where we keep our 100,000 other COOKFOX employees, our 2 honey beehives. I'm the beekeeper at the firm, and you know, for 6 or 7 years, I've been keeping these 2 beehives. You know, we maintain the hives. It's a great way to teach about ecosystems, about sort of the environment around us, and it's also a great way to get sort of everybody involved in you know, extracting the honey and learning more about honeybees. So the next project, 512 West 22nd Street. This is LEED Gold office building on the High Line in West Chelsea. It's clad in black terracotta by Boston Valley Terracotta. And you know, the design is really inspired by some of the historic industrial warehouses of West Chelsea. All the floors have a unique terrace that they have access to. And the building is located along the part of the High Line called the Chelsea Thicket, which is a unique part of the High Line that is planted with the diversity and the density of a forest. So it's one of the few places in the city that you can look out and look into a forest. And so this is an exterior staircase at 512 that looks out through the forest into the larger city. And you can see we have stepped design so that all the floors have a unique terrace. The plantings on 512, are drought-resistant native species that are really designed to support native ecosystems, and that's really important because that allows the support of native insects, butterflies, birds that have evolved alongside the native plants and other ecosystems. So that's a really important part of plantings in our landscapes. And then the other part are some of the curved glass in the facades, taking away from the interior, taking away the corners. Really allows sort of a full panorama of the city. It doesn't stop. The view doesn't stop at a corner and continue on the next facade. It really stretches around. And this is the view from the 7th floor terrace looking down on the High Line. So the next project, St. John's Terminal. This is a 1.3 million square foot Google office building that's currently under construction. It's adjacent to Pier 40. And this was the terminus of the High Line, the original terminus of the High Line. So the trains would come in on the 2nd floor. They would be unpacked and put onto trucks on the ground floor and then shipped around to the city. So what we wanted to do was maintain as much of the existing building as possible and then add on what we could above it. So you'll see the bottom podium, we took the top off of that and then added another overbuild on over top of that. And we also sliced off about the north third of the building and left this kind of section through the building that leaves the concrete and steel structure, the rail beds exposed, and becomes a public plaza. At the setbacks, there's lots of terraces, and this gives people a lot of space for recreation. All right, so the final project, was sort of a collaboration between a lot of different groups. It's COOKFOX, Borough Hatfield, and then it's teamed up with Boston Valley Terracotta as part of the Architectural Ceramics Assembly Workshop. We were given the opportunity to really have a broad range of being able to design without the limitations of a budget, a project, a client, site, and really take a lot of the ideas of native ecosystems, understanding sort of the impact that our construction has on the built environment, and really try to combine that into some sort of physical mock-up. And it really was an exploratory project. So we started, really just looking at a bunch of different prototypes, modules, modeling out, different ideas. Refining some of these modules, and the idea was to really play under the strength of terracotta and architectural ceramics and the materialities, and one of those is a ability for sort of rapid and affordable prototyping. And so the idea was to do a kind of standard stacking module, repeating pattern that, by rotating these modules allowed for sort of a variation across the facade. And with that, providing sort of voids, which then program could be inserted into. And so we looked at how we could incorporate program into these modules. So we created a birds, bees, and plants pod, which played off of the orientation of these modules, to help with the design of the with the attributes of the program. And so you can see here the pieces together. And the backside of these modules, the idea is that the modules are entirely are all exactly the same, but then through a simple slipcast pod, you can insert them into the back and have different programs. So starting with the bird pods, we have this kind of orange, red slipcast terracotta pod that gets inserted. The birds have a pod that allows for proper ventilation, drainage. The entry size to the nest is actually really important to promote the correct type of native bird species and not allow some of the other aggressive non-native species to attack them. For bees, the pod was sort of a vessel in order to hold these reeds. So these are a solitary bee. So these are there's dozens of types of solitary bees in any one location, and what we're doing is just providing habitat for these bees to come and nest in these reeds. So at the top you can see is a typical reed where the bee will lay an egg, the female will provide food, pollen, and then will provide a cap and kind of fill up a single reed all the way down. And also providing different size reeds and tubes also gives a broad range of habitat for different types of native solitary bees. And I should mention that solitary bees don't produce honey. They also don't have stingers, but they are an amazing pollinator. These bees have evolved alongside the plants of an ecosystem, and so they are the single best pollinators in any given location. And then finally, a planter pod. So, the idea was to use some of the attributes of the screen wall. And, one of the ideas was that it could collect water. It could be a passive irrigation system that uses the idea of a bottom watering planter. So it's a double-walled slipcast vessel, which the bottom container collects and holds water, and then through a wick and through some of the porosity of the ceramics would water the soil as needed when it dries out. And then if there's too much water, then the reservoir will overflow and drain out the back. So through the exploration, we looked at a lot of different glazes, worked with Boston Valley and the Matter Factory to really explore a lot of glazes. We ended up really kind of liking this blue engobe, but colored clay, and also so pairing that with a white glaze. And this was sort of a quick rendering of what that might be. Looking at the module itself, we wanted to play off of some of the abilities of glaze to flow and break, and really try to understand some of the luminosity of the glaze itself. So then this is just a quick mock-up of the structural components. It's a dead-loaded system attached together with bolts and load-bearing. The idea of how this might get implemented, just as a knife plate, it's being put in front of glass. It could be freestanding, could provide a screen, which might also, act as a way for benefit bird collision mitigation as well. And a quick study of how this might look on a larger building. So when we came together to put this together, the group went up to Buffalo, to the Boston Valley assembly plant. They had fabricated all the pieces and cut all the pieces. You can see here the pods. They're made of a similar clay body, fired a little bit differently, and fabricated through a slip cast process. You can see the bird pod with its piece open. We had gone up, and our group sort of assembled this piece together, and then you can see sort of the final assembly. With the plants, birds, and bees. Here you can see it outside, really playing up the different the tonalities of the glazes and the different pods. And here are the 3 pods close up. Looking at some of the plants. And the idea of the planters also is to collect seeds from the city, really not to be so controlled with what plants are there, but also collecting some of the native grasses that might blow in on the wind. Here you can see the section through the plant pod, looking at the reservoir below and the backside of the pod. So, thank you very much. Thank you for your time.
Thanks, Spencer, for that interesting presentation. I think it's always fascinating to see when we start to delayer the facade to see what other kind of function we can provide within the living system. So thanks for sharing that experiment. The next presentation is from Erleen Hatfield, managing partner from Hatfield Group, and Manan Raval, principal of facades and special structures, to talk about resolving complex geometries.
Thank you. Oh, thank you. Here's our timer. All right, you got the clicker?
This is next, this is back, this is the pointer.
Got it, thank you. So thank you and welcome everybody. I'm not quite sure how you go after somebody who has beekeeper in their title. That's really cool, and I think if you ever get a chance to go to COOKFOX's office, it's really interesting to see the bees out on the terrace. It's really very interesting. It's cool. So I'm Erleen Hatfield, and this is my partner Manan Raval. We're with Hatfield Group, and we are going to talk about complex geometries today. And we're going to use this Halo Tower, a building that's under design in Newark, New Jersey, as an example, a bit of a case study.
So first, just a little bit about Hatfield Group so you know where we're coming from. We design all kinds of structures. We have quite a long history, and not only in the building enclosure space, but also long-spanning complex structures. We do all kinds of advanced processes. We like to but we like to use Rhino and Grasshopper, Dynamo, things like that. So it's embedded in our DNA. And we work on all kinds of different projects, even though we're talking today just about a multifamily residential project. We also are doing cultural projects, academic, mixed use, a whole host of different types of projects, athletics, sports, and residential. Oh, I think this slide's missing a 0 in there, but we've done a lot more than 15 lead projects. But sustainability is a big part of our DNA, and we'll talk a bit about that as well. And just so you know, we're a women-owned business. Hatfield Group has been in existence for just about 4 years now. It's not only women-owned and women-led. And so to talk a bit more about the technical details of how we tackle our facades projects, Manan, you want to go through this one?
Here is the
Yep, the green. One. That's the next
one. So this is the complex geometry, resolving complex geometry. As you know all, we need to all this design, the parameters we have to consider. I'm not going to through in this workflow, but this is the one, the geometry, the resolving geometry, the workflow. Mostly the things, you know, the architecture's design intent, ownership also there. Here, so this one, as well as we need to consider the design parameters that include all this, the points, definitely the performance parameters, and how that we deliver, because that code compliance and the budget also, because this is in Newark and it's very cost effective. The client and as well as the architect prefer to come up with the cost effective facade. The project schedule and buildability and the materials availability, because during the COVID times we see that a lot of the shipments, the delay, as well as material is not available. So those all I think we need to consider, and that all we during this design, you know, happen is still going on. I mean, it's almost done, but we consider this is an important point, and based on that we come up with all these documents and we submit to the contractors, which is the Hudson Meridian is the CM for this project, and now it's going to the tender documentation. So this is the the case study here, the Halo Tower. It's in Newark. You see that here, the Newark downtown. You want? Oh, go ahead, Erleen.
Not only is it downtown, but it's near. Whoops, make sure this is on. It's near the city. It's close to the airport. There's this whole new master plan development that was announced earlier this year in Newark, and so the site context is really important. It's in Newark Central West, near Rutgers. It's near the Essex County College. It's near that new teachers village, that solution for teacher retention in Newark. It's basically subsidized housing in the center of the city for teachers. So you okay?
Yeah, sorry, I'm fine.
Okay.
So yeah, here's the Hello Tower. It's a 3-tower, 38, 42-story, as well as a 42, 46-story tower. It's almost 900,000 square feet altogether. It's the highest building height is a 565, and that includes the automated parking, the terraces, garden level amenities here, this here, there, as well as here and on top, as well as the roof to pole all the way to the tube. You're going to see that at the top. The completion date for these towers is 2024. So yeah, this is a street for the presence, and there are 4 types. It's kind of the complex geometry. Here you see that all this, the metal panel as well as the terracotta, the screen, all this, how it's a complex geometry, and we come up with the 4 type of the systems. It's part of the unitized curtain wall systems with the metal panel, with the GFRC, as well as the stake built system. So here you see that it's a facade slice that here. It's a step, the step terrace here. This one is the stick built because it's not in the same plane with the curtain wall, the unitized panel and
it's also curved.
Yeah, it's a curve too. The curved glass here, that's the architecture preference, as well as the hang here, and as well as the cantilever for this. And then the main thing here, I'm going to talk later on about that. This is we have considered the 6 feet, not the standard 42 inches the parapet. So here, the architect prefer the metal band comes nice and clean, neat, and a marry with the unitized curtain wall like that interface here, as well as that this curtain wall, the below tower, where it's a slice here. It's also the metal panel band at the top. That's the architecture design intent. So what we have come, we come up with the design here that this curtain wall hung from the top. However, we definitely need the lateral support for the structure stability as well as the weather tightness. Water, the air will not go to the upper apartment level. Same thing, this curtain wall is below. However, this top portion is the cantilever, and which attached to the top of the splice joint here. But the main thing we need to, because of the wind is so high, I believe around, I think this area, we receive probably 70 PSM. It's range based on the wind tunnel study. It's range from 70 to 110 PSF. We come up with some 3D, like, the drawings, how this interface, the sky garden, that how curtain wall interface at the stick built system, as well as how we design and how it looks like that the steel beam running here, and also that here to support this curtain wall, the above as well as the below. This is a stick built system, so it's very straightforward, but we need to consider that how the unitized curtain wall interface with the below grade, the sky level, the sky launch, the system for the weather tightness as well as the structure point. There are this slice geometry here. You see that the step facade. This area is the podium level where the metal panel protrude and interface with the louvers as well as the metal panel system below level, the podium level. And this is a incline and a slope panel interface with the unitized curtain wall system. You can see that here too. So this is a very critical detail here, and we develop how this unitized curtain wall panel and this incline, the slope panel marry together. And you see that here, so this is just a generic detail. It's not it's an HD level detail, but we come up with the curtain wall, which is above level, and then this below is hung. But however, we need to come up with the the support this framing, and we come up, I think, this steel beam here. It's a generic, but then later on we suggest that to put it here based on a discussion with the structure engineer and us. So it's inside within the soffit, and how that interface this panel system to the stick built system. Here also
the inclined glass.
Yeah, it's a slow inclined panel, and generally the code, I believe it's a 15 degree. If it is more than 15 degree, then you need to comply with the slope glazing requirement, and that definitely you need to provide the overhead glazing like safety, which include the laminated and all. And we come up with this slope, like the slope glazing around, I think, 13 degree. So that's where we can eliminate, to use the laminated, the glass overhead glazing, and it's a very effective way to do that. Also, this is the curve. It's a kind of the train now at the corner. Architect prefer ownership for the visible transmission, maximize, the visibility. The challenge here is the concave and convex, that there are also the low-E coating available in the market, and soft low-E coating all available on concave surfaces. So we coordinate with the Guardian, we coordinate with Saint-Gobain, and finally we establish that material available at the low-E coating, because this is going to be fabricated sooner this year. So we have selected Saint-Gobain glass as a basis of design. It's a Cool Light Extreme 70, which maximizes the visible transmission as well as the lower solar heat gain coefficient. Here, I mentioned that this is a rooftop. The challenge here, you see that it's 100 PSF and 110, and it's a rooftop structure. Sorry, I'm in the pool here. So, based on the wind tunnel study, this is a not comfort level with the high wind pressure and here. So we come up with the 72 inch to 84 inches the panel here. So that way, these people, I mean, it's not feel like, during the high wind, or because the goal is to use, is continuously, not to like, during the not high wind pressure. And we come up all this, we suggested to the architect we definitely need, but that impact, the zoning too, because if you go more than 42 inches, that part, covered into the square feet of the zoning. And this is the, I think we missed the
okay. We updated our slides, but I don't think they got updated. We had a few more slides in here, so maybe we could just talk a little bit about with complex geometries, this building has a number of different systems: curved glass, inclined glass, right, stick-built systems, curtain wall systems. It's really got quite a number of challenges, and really trying to tackle those challenges early on with systems that are as cost-effective as possible, looking at different procurement paths, maybe looking at vendors that aren't, or suppliers that aren't necessarily the ones that you may think of on first pass, but looking at alternate sources. We did a project recently also in New Jersey where all of the materials were sourced out of Dubai.
From the Dubai,
with Saint-Gobain glass, and with a lot of oversight and supervision to make sure the owner was getting the quality that they wanted. But procurement issues are definitely an issue, a concern right now around all of these things. But the idea of having this much complexity in a building and this many different conditions, and really trying to do details early on to define the scope and have accurate costing information, bringing suppliers in early to help make sure that the details are coordinated with their systems is very important.
Yeah, it's very important here, like, because this is a super high here, so definitely you need a backup structures, and how you're going to do that.
Reinforced
reinforcing within the curtain wall system with the clean and neat look, or you're going to do the steel skeleton structure here. So this, there are a lot of, I think, the geometry you can resolve during the design phase.
Exactly, and most importantly, the slide that we get skipped in here is the architect is INOA Architecture. Beautiful design. Murat is the architect there, and just full credit to them for the design of the building. And anything else, Manan?
No, I think that's it.
All right. Well, thank you all very much. We appreciate it.
Thank you.
Thank you, Erleen, and thanks, Manan, for the presentation. So the next topic is the next speaker is going to talk about interlayer selection. And I myself is a little bit of a science nerd. I like to read material science news and know that there's actually a lot going on in that community right now. So I'm excited to hear from Alberto Alarcon, the marketing manager of Crowray, to see, what other new developments and what are the current developments in the interlayer selection. As we know, a lot of projects wouldn't be possible without their appropriate selection. So with that, Alberto, I'll pass it over to you.
Easier.
Oh.
Thank you. Thank you very much for the introduction. So I want to say I'm really happy to be here today. This is one of the first events we have in the city. It's really good to be back again here. So today I'm going to talk about interlayers for laminated glass, different applications, and I would like you also to show you some projects about the city that use laminated glass. We have a tabletop outside. If you have any question, I will be there. We have 3 experts on laminated glass over there, so I will be happy to address any question you have about laminated glass. So it's about laminated glass and how to select the appropriate interlayer for laminated glass. So I love glass. I need to say that it is a very interesting material. You know, it can isolate, and at the same time, it's an almost invisible material. It separates, and at the same time, it integrates to spaces. And I mean, it's a mystic material because it's born from the earth and fire, but remains sky and air. So I really like glass. It's a great material, a beautiful material. But it happens that something is a fragile material sometimes. So it happens that sometimes it breaks. And there are many reasons for that, like, you know, spontaneous breakage, the particles, inclusions on the glass, and there are other threads that they make glass break, like natural threads or even human threads. So sometimes tempered glass is not enough. There are some other threads we have, and it also, you can break glass accidentally, or you can and for human threads. So that's why we have laminated glass. Laminated glass is sandwich, it's simple. It's a simple material. It's 2 pieces of glass stick together with an interlayer. This interlayer, there are different technologies like PVB, ionoplast entry glass, EVA. There are different materials, but the main purpose of this interlayer is to stick together these 2 pieces of glass and protect in case of a breakage. So it protects for you know, flying glass and because I mean in the past video it was like it was fun, but sometimes it could be a very serious matter. So that's why we have laminated glass. We can add more plies of glass, more interlayers, and then you can have a multiple laminated glass. So due to time, I'm going to talk about 2 different technologies. One of those is PVB, polyvinyl butyrol. This polymer is a flexible material. It is excellent for safety glazing. It comes in a very different colors, and also it filters 99% of the UV light. So that's a very good thing on PVB. It can be printed, it's available in different thickness, and it also, because it's a flexible material, it can dampen noise. So you can improve your STC values for acoustic applications. And then, I love this project, by the way. And then we have century glass. Century glass is a different chemical composition. It's a stiff interlayer. So the benefits of using century glass is the clarity. It is as clear as low iron glass. So when you have this type of application, it's excellent. And other thing we have is that you can use it with, you have open edge. When your edge of the glass are exposed, because it don't have plasticizer inside in the formulation, it could be exposed to the water. So you can have these really nice views with the glass, and it also filters 99% of the UV light. And I mean, it has one other thing it has is that the post-breakage performance is excellent. It's a stiff interlayer that can be used for this type of guardrails because it's a stiff interlayer. And I will talk a little bit more about that in a few minutes. So with these 2 interlayers, we can do a lot of things. We can use safety glazing, we can make decorative applications, we can improve acoustics, and also we can do safety and structural glazing. There are other types of applications like UV light filter, or sometimes you need UV light to come into the building, so there are other materials. So you can see there are a lot of materials, and that's why we develop this, we call it decision tree. It's a flow chart, so you can see in the green diamond, you start here, and then you need to make selections if it's exterior, interior applications, structural glazing, if you are dealing with lower glass, if you need any acoustic performance. There's a QR code. You can download this flow chart in your cell phones, and it will take you to different applications and materials. There are something this chart doesn't cover, like security applications, hurricane or tornado applications, but we have another tool that will help you with that. So if you have structural applications, like in this glass railing below support, when you have a PVB interlayer, I said it's a flexible interlayer, but it happens that if the glass breaks, it will not retain the glass. With center glass, you can retain the glass because even the two pieces of glass breaks, the interlayer is stiff enough to carry the weight of the glass. So with this type of application, you prevent the falling, and also you're preventing the people that walk beneath this glass railing. So, here. So in this chart, in the red line is PVB, the blue one is center glass. So you can see this is a time versus displacement. So you can see, and this had a lot of 30 kilograms. So at a certain point, PVB will fail, as in the video, but with center glass, it will hold the weight of the glass and we will in place. So that's why when the glass breaks, it is still like be safe, and you can replace it whenever you get the next piece of the risk replacement. So that's why it is very suitable for this type of application, skylights and slow facades. That's why we select this interlayer. Or if you have minimal support glass, like here in this application, you can see if the glass breaks, it will remain in place. So that's the benefit of using center glass. By the way, in this project, center glass is printed on the interlayer for giving some shading and also some bird-friendly applications. There's one more thing I want to say about PVB and center glass. So if you saw the previous chart, center glass is 5 times tear resistant than PVB and 100 times stiffer than PVB. So I'm not going into the details, but what I want to tell you is that when you use center glass, you can reduce the stress on the glass and you can reduce the deflection of the glass. That means that you can optimize your facade, you can remove weight from the facade, and like in this application, you can start playing with bigger pieces of glass, with thinner constructions, and doing structures also with center glass, like the Apple Cube in the Fifth Avenue, or the glass stairs in the Soho Apple Store. And then you can start playing, you can start designing with more freedom. So this is a very cool seesaw playground from EOC. They designed for the GlassTech last edition. So it's all made by glass and center glass. Well, maybe you don't need the structural requirements. You are only dealing with low iron glass. So there's a very good option. If you don't need structural requirements, if you have low iron glass, you're paying for a clarity of the glass. You don't want to put any tint on the glass. Standard PVB is kind of yellow. Sometimes it has a blue tint or green tint. But there's a special interlayer that is called Ultra Clear that is a very good option to use for low iron glass application. When you have full capture systems, when you have any structural requirement, this is a very good option. So you can see Sentry Glass. This is the yellowness index. We measure the yellowness of the interlayer, and then we compare it. So you can see that Trusifol Ultra Clear is almost as clear as Sentry Glass. The standard PVB should be like this yellow, so the lower rate of the yellowness index, the better. So there are applications that, for example, here, you don't need any structural requirement, just safety glazing. So having ultra clear PVB is a very good option because also you're filtering the UV light and you can protect from sun damage all these luxury items. This place, I love this place, the TWA hotel in the JFK airport. So in this project, there were two specific concerns: noise and optics. So in an airport, you have a lot of low frequencies, and the way you reduce the noise with low frequencies is increasing the mass of the glass. So you need to have very thick glass, multiple plies, and what happened with that is that you start, if you don't use lowering glass, this glass will look green. If you use a standard PVB, because you have different plies of interlayers, you may see yellow or any other different tints. So in this construction, they use 3 plies of interlayers, 4 plies of glass, and that way they reduce noise because the interlayers and the mass of the glass, and you have a very good view, very clear glass. Now, if you're dealing with isolation, you have requirements, STC requirements. There's a special interlayer, very flexible. So it's the opposite to the structural application. It's very flexible material that can damp noise in 5 dBs. So just by placing this interlayer, you can reduce on 5 dBs. I mean, the dB scale is like a logarithmic scale, so 5 is like twice the double energy of sound, so you can reduce 5 times. I'm showing you a video. I don't know if sound is working on videos, but here, this is a project we have in Chicago, IG unit, double laminated. Okay, it's not working, but you can hear all the noise here, all the high and low frequencies, and then when you close the window, you're supposed to not hear anything. But there are different projects here in New York, like the Pier House, Brooklyn. All this residential building is with Trusifol sound control interlayer. Then we have colors. We have a very huge portfolio of colors. We have a very unique colors that is called brilliant black and diamond white. There is these interlayers are 0% transmission light, so you can start playing with decorative application, like here in this. This is the. I'm not supposed to say it, but this is the Amazon headquarters in Seattle. Oops. So here we have these glass fins. So it is interesting because depending on the side you place on the block, you will see all these fins white. If you walk to the opposite block, you will see all the yellow of this glass. So this is possible because this diamond white interlayer is 0% transmission light. So you can see any yellowness in the white side. So that's certain thing you can see. Here below you can see the canopies. It's the other version of Sentry Glass, translucent white version of it. It's very popular in canopies. Almost, if you walk around the city, if you saw a translucent white canopy, is Sentry Glass. But also I said that there are some applications you don't need security, you don't need, the requirement here is UV light. So you don't want to block UV light in this application because it's a botanical garden, so you need UV light for plants to grow, make photosynthesis, and also there are other applications like zoos, There are some hospitals that also want a little bit of UV light for us to synthesize vitamin D. So what doesn't cover this flowchart is all the security glazing, human threats and natural threats. So there's a lot of applications like ballistics, bullet-resistant blast, tornadoes, hurricanes. And in this video, we are showing this is part of this test we made with, this is quarter-inch anneal glass, 180 mils of century glass, and quarter-inch of century glass of anneal glass. So you can see here that is, they have shot it 5 times. They kick it, they attack the glass with different tools, they throw some bricks, and in this test, it lasts like almost 10 minutes long. So this is only the last part of the video, but you can see that it can retain the intrusion. So when you have security applications, you need to gain time. So that's the big thing with security glazing. You need to buy time for someone to react to that threat. So we have a brochure you can also download, or we have some printed copies outside of different construction of glass you can do. So this is a regular safety glazing. We can use here 35 mils of PVB interlayer, and if you have an attack, it will resist less than a minute. Then you have enhanced 4 centuries, so you're getting thicker in the mass of the interlayer. All these plies of glass are quarter-inch anneal glass. So if you see, the thicker you get, the more time you gain. And then you can do multiple plies of glass and interlayer, and you will start to gain a ballistic protection. So in the video we saw, this is a very similar construction to this, but now this is for hurricanes applications. So this is the missile test. This is a 9-pound missile, 2x4, 80 miles per second, impacting the glass. That's the level D test. And with this type of construction, you also gain hurricane protection. Tornado is a different thing. It's like this test, you will need a 50-pound missile, 1 miles per second, impacting one of the corners of the glass. So this is a very impressive test. And again, for this application, you will need an IG unit with very thick glass and also a structural interlayer. We have one unique material. I mean, all of our portfolio is like interlayers, but we have one material that is go outside the glass. In the last surface of the glass, we used to have the CPET interlayer. So this is a hard coating to protect from spatials when the glass breaks and there are some small particles of glass flying, and it will protect. Even the glass is break, you can touch the surface of the broken glass and you will not hurt. So we made a different texting for that one. So this is our decision tree. Again, if you scan this QR code, you can saw this in your cell phone. And we have another tool we recently launched. It is the Solution Finder. So this application, you can use it on your cell phone. And, well, sun is not working, but it will drive you to 5 questions. So I really like this app because it's like a hub for all our portfolio materials, all our brochures, all our newsletter, all our press release. So you will have all the brochures here, and also it will, if you select the wizard tool, it will ask you 5 questions, and with these 5 questions, it will drive you to the correct interlayer. Like the first question, do you need structural performance, or are you dealing with acoustic requirements? You can try, it had some examples of how this interlayered sound control, interlayered sound, and also, colors, have some examples about our colors. You can change the color in this application, and UV light is also, if you have IG units or you have low iron glass, it's like it will drive you to the correct interlay again. And then it will give you the answer of the interlayer. And then it will drive you to different tools we have online, glass calculator, sound control estimation, or some other tools we have available. So you can download this app using this QR code. And again, if you have any question related to laminated glass, PVB, century glass, or any other interlayer, you can find us outside here in our top table. So I left 30 seconds to the next one. So thank you very much, and I hope you enjoyed this presentation.
Hi. So our next speaker is Bob Dirks from AkzoNobel, here to talk about the life cycle assessment and the relationship to powder coating.
Good afternoon. Sorry, I'm just going to move that around. I hope that's not a problem.
Here you go. Next back pointer.
Next back pointer. I got that. Thank you. All right. Good afternoon. Hope you're all doing well. And I hope the people leaving right now, that's not personal. So moving into a presentation today, standing the test of time. I don't have any fancy videos, but I do have a nice story to tell you. And it's a story about a young couple named Lauren and Sarah, living in Brooklyn, just on the other side of the river. They love living in a vibrant city, they love the art scene, love being outdoors, but they also care about the environment. And they are trying to take care as much as they can within their city life. So they ride their bike to work when it's possible. They try to eat vegetarian a couple days a week. They grow their own veggies in their little front porch. But for some of these choices, it's very easy. Don't take very long showers, right? But for some of them, it's not that easy. Actually, it's quite hard. With a very hectic life in the city, as all of you know, shopping is not always planned. And since the ban of plastic bags in New York City in 2020, it's hard. You got to bring your own grocery store every time, right? But as it is unplanned, sometimes you end up buying a new bag anyway. Sarah has decided to buy cotton shoppers and take those, try as much as possible, back to the grocery store over and over again. But also here, she does forget her bag sometimes. Lauren is a little bit more skeptic on that, because is it really better for the environment to keep buying new cotton bags over and over again if you're not reusing them so many times? Because isn't cotton a more difficult substrate to create than a plastic bag? And those are actually the right questions to ask. And getting the answers is not that easy. The only thing that is easy to realize for yourself is that using anything only once is the worst thing you can do. And we've heard that before today. But to fully understand what is the impact of either a plastic bag, a cotton bag, or of any other material, you have to look at a whole life cycle of a product. You have to look at the raw materials that are put into it, the number of times you use it, and what do you do with the material after the useful life of that asset, in this case, the plastic bag. Analyzing something like that is called a life cycle analysis, and we've heard that before today many times. And conducting a life cycle analysis is very difficult. Whether you do it for a plastic bag, a cotton bag, a pair of shoes, paint, coatings, or a whole building, it's hard. It's hard. We've seen some very impressive calculations today of embodied carbon, life cycle analysis of whole buildings. Those calculations weren't done overnight, and I'm sure some of you in this room are working on those calculations and can only back me up with that. So when you want to conduct a life cycle analysis, you first want to learn and understand about the situation. Then you want to create transparency, so what are you actually looking at, followed by taking action on how can you then improve and reduce the environmental impact. So let's have a look at how we are doing that at AkzoNobel as powder coating supplier. So first of all, we start with learning and trying to understand our value chain. We're looking at 3 different scopes of emissions, scope 1, 2, and 3. Scope 1 and 2 being our own emissions, so the manufacturing of the paints and coatings, the energy you use with that, and the carbon emissions that you emit by manufacturing your own powder coatings. Then you have scope 3, which is going on 2 directions of us. The one side, we have our upstream, who are the raw materials, what are the raw materials that we are using, and what are the carbons that are emitted during the creation of that process, and also the transportation of the raw materials into our factories. But we're also looking towards our customer sides. So how are we then transporting our powder coatings to our customers, usually extrusion companies, job coaters, fabricators, who are then applying the powder coatings? How much energy does that take? And that are curing the powder coatings, which is one of the, of course, energy-intensive parts of our process. Creating that transparency, again, is just the start. Sorry. As AkzoNobel, we have committed to the Science Based Targets Initiative, which means that we're going to take responsibility for not only reducing our carbon emissions in scope 1 and 2, but also taking responsibility for the carbon emissions in our scope 3, our suppliers and our customers. And we will reduce that by 50% by 2030. Now, that's a good start. But let's see how we are showing that transparency. We are doing that through an environmental product declaration, and also that has been mentioned before. So an EPD is showing the entire environmental performance of your coatings, our powder coatings in this case, throughout the entire process. And we have this available for all of our powder coatings that end up in the built environment. Whether you want to use a durable system, Interbond D1000 in our terminology, for your fencing or your railing, or an Interbond D2000, which is more durable, or Interbond D3000, which is our hyper-durable system, we have the full transparency of that available for you. Now, transparency sounds nice, right? But that's just a start, because you may just show that your environmental impact is terrible, but you still get points for being transparent. We don't accept that. For us, that's not enough. So we are taking action to try and reduce our carbon footprint continuously. So how do we do that? First of all, by providing longer-lasting solutions. So how do we coat the substrates on your buildings in such a way that they can last longer and longer? Secondly, by trying to have lower embodied carbon than liquid paint solutions or than alternative substrates. And lastly, we're trying to provide continuously innovative powder coating solutions that do deliver energy savings in various ways. As the world leader in powder coating since 1972, and yeah, that's right, I read that in the books, I wasn't born then yet, we have the best warranties in the industry, offering up to 30 years of warranty according to the standard AMA qualifications that are well known to all of you. We continuously have innovative collections, colors, and on-trend designs that are in the minds of the architects. We have several track records to prove that performance. So now let's have a look at those 3 actions that we are taking to continuously reduce our environmental footprint, and which are the track records and the products that we have for that. So firstly, we are continuously providing increasing, longer-lasting solutions. So we have 2 different ranges that we're particularly promoting and that for us are the new standard in the industry. These are super durable and hyper durable solutions. For that, we have different track records. So the first one is Richmond City Hall that was built in 2004, and we have with that the first hyper durable track record on powder coatings worldwide. Now, what is it, 17 years later, that is still proving to be a solution that works, because the window frames that are powder coated on the side still have the same color effect as they were upon installation. By using a more durable coating solution, you also reduce the cleaning and the repair needs for the building, and thus you're also reducing the environmental impact because you're reducing the water that you use to clean, the cleaning detergent, etc. Then we also have many actually track records in the area of our super durable solutions, which is our most used product in the market. So this is meeting AMA 2604 standards and are very suitable for projects like the iconic Shard in London, where you don't see where the facade isn't the main aspect of the building, but where still the coating is supposed to stand the test of time. Secondly, we are looking at products that have lower embodied carbon than our liquid paint solutions. Why does powder coatings have a lower embodied carbon? Does anyone in this room know? Maybe I should answer that for you then. So there are no VOCs in powder coatings and no solvents. Also, there's less waste than in liquid paints. Because I'm not sure if all of you know how the powder coatings process works, but you electronically charge the substrate that you're trying to coat, as well as the powder coating, and it sticks to the surface so it doesn't fall off. For the parts of powder that do fall off, you can reclaim it and spray it back onto the next round of application. And so there's much less waste as in liquid paint, where of course the solvents evaporate into the air. There's also improved coverage and more resistance, which means that during the transportation and handling of the there's an echo, sorry. During the transportation and handling, there is less defects, and you have less cost to replace certain parts of your windows and doors. The costs of powder coatings are often perceived to be higher than liquid paint, but in fact, when you consider the entire life cycle and the entire elements of a coating job, then the cost levels are the same. And overall, and here, of course, different life cycle studies come into place, but overall it's estimated that powder coatings can save up to half of the carbon emissions, so the embodied carbon, compared to liquid paints. So next to those benefits compared to liquid paints, we're also with powder coatings increasingly able to mimic natural metals. And I want to show you two examples of that. So the first example is a powder coating that can mimic natural woods, which means you can avoid the depletion of natural materials for the facades and also reduce the cleaning need of your facade at the same time. There's different techniques to make wood effect with powder coatings, and we're happy to explain that in more technical detail to you at our booth outside of this room. The second example is a stone effect. Stone, we've heard before today, is a very popular building material, though it also has its downsides. It's heavy, it's expensive, and it's difficult to install, especially on the higher-rise buildings. We have a range of powder coatings available, a super durable range that does mimic natural stone effects: limestone, Portland stone, or cement. And concrete. This will give you a comparable effect to stone as you would like to reach, but then cheaper, easier to install, and lighter, and thus also lowering the impact of the transportation cost, for example. Thirdly, our powder coatings can also help by reducing energy. First of all, we are aware that curing the powder coatings is an area for improvement for us, and we are continuously working with our suppliers to try and develop coatings that you can cure at lower temperatures and thus save energy. Also, powder coatings is applied in a single coating layer, so not multiple layers, which also is reducing energy, of course, when comparing to 3, 4, or 5 layer systems. And lastly is a very nice innovative solution that we have, which is called a low solar absorption powder coatings. And that is best told by sharing a track record with you of the Solar Innovation Center in Dubai that was opened in 2018, winning LEED Platinum standards. And by using our low solar absorption technology, it means that the inside temperature of the building can be reduced up to 3 degrees Celsius, I owe you the Fahrenheit degree of that, and up to 7 degrees Celsius of the outside, especially if you look at okay, this building doesn't have a roof, but if you look at a roof of a building that's absorbing a lot of sunlight, you can reduce the temperature of the outside of the building. So, in sum, how can powder coatings help you to reduce your environmental impact? We can provide lower embodied carbon compared to liquid paint. We can provide energy savings compared to other solutions, and we also provide longer-lasting powder coating solutions to you. And just like the coatings, in case you're wondering about the bag, Lauren's study showed that indeed it's very hard to determine which of the bags is most sustainable to use. In fact, the bag with the most durable system, not the cotton bag, but a chemically created more durable bag, is most sustainable, but only and only if you keep reusing it. Because in the end, the most sustainable thing is to keep using it. Thank you.
Thank you, Bob, for that presentation. I think you definitely answered one of my questions in terms of the studies into the curing process, so very happy to hear that's underway. So the next speaker is from AGC Chemical to talk about FEVE, fluoropolymer resins. Winn Darden.
Thank you, everybody. I appreciate you all taking the time to come out. Oh, there's my biography. Not much to read there, I guess. There we go. Oops. Yeah, this one, right? There we go. So I'm going to talk today about environmentally friendly FEVE resins for powder coatings. I'll explain FEVE upcoming here. So FEVE is the name of the polymer that these materials are made from. And just like many polymers that are used, we name this after the raw materials that are used to make the polymer. So FEVE stands for ethylene, and that's the blue circles that you see there. And vinyl ether, or VE, stands for the vinyl ether segments, and those are the green ones that you see up there. The fluorinated polymer portion of the polymer, the fluoroethylene, gives you the weatherability and durability that you're looking for in a powder coating. We'll also offer chemical resistance, the ability to be more cleanable than regular coatings, and some other advantages as well, but this is primarily why people are using these. What the vinyl ether segments enable us to do is to have a gloss, higher or lower gloss, make these materials soluble in solvents or compatible with water, and it also provides cross-linking. That means that these resins can chemically react with materials called cross-linkers to form a very hard, durable finish. What are the features and benefits of FEVE? Well, the first one, the fluorinated units provide outstanding UV resistance, that is to UV light. Everybody's familiar, if you ever paint your house or if you do that, you can walk up to the house after a couple of years, and if you rub your fingers on it, you'll see the paint coming off in your fingers. What that is that the ultraviolet light is degrading the surface of that paint, and eventually the paint will go away after some period of time, hopefully after 8 or 10 years, so you don't have to repaint it every couple of years. What are the benefits of this outstanding UV resistance? Well, long-term durability is one. These are coatings that will have good gloss and color retention for 20, 30, even 40 years.
There are no chalking on these coatings. You won't see that hazy, off-color material forming on the surface of these products. And these products will enable the coating formulator to meet the weathering requirements of AMA 2605. So that's 10 years of South Florida with greater than 50% gloss retention and less than 10 or less than 5 delta E or change in color. These products can be made into a range of finishes, from flat finishes to matte to semi-gloss all the way to high gloss. You're not restricted to an intermediate gloss like some of the competitive materials are. What this means for an architect is now you've got something that's very flexible and versatile in design. You can have parts of a building that are low gloss, parts of a building that would be high gloss if you wanted to catch someone's eye a little bit more. These are cross-linked materials, as I mentioned earlier. Well, what that means is they have good mar and scratch resistance. There'll be less damage to these coatings as they're moved from the job site and being assembled on the job site. They offer good corrosion resistance. This means that they can be used in a range of applications, this ranging anywhere from seacoast, where corrosion is a big issue. The liquid coatings of these products get used on bridges where road salt is used, so corrosion is a big issue. And finally, these products can be applied in the field or, in the case of powder coatings, applied in a factory. So that means you can use these for new construction, or you can use these to rehabilitate structures as well. So now let's talk about FEVE powder coatings versus liquid PVDF coatings. PVDF, of course, is the best known fluoropolymer. The trade name most people know is Kynar. FEVE powder coatings, just like liquid PVDF coatings, are ultra weatherable. That means they stand up well to the environment over very long periods of time. These, again, are cross-linked coatings. They have good mar and scratch resistance. Well, PVDF liquid coatings are thermoplastic. That means that they melt to form a film instead of chemically reacting to form that film. So they're more susceptible to mars and scratches during handling. FEVE powder coatings require no primer on the surface. They can be applied directly to treated aluminum. Or steel or any other metallic substrate. Whereas PVDF liquid coatings are applied to primed metal, so there's an extra step involved when you use a PVDF coating. Powder coatings can be recycled. That means the usage efficiency can be greater than 90%. Recycling is not possible with PVDF products. The powder coating, the FEVE powder coating, contains no solvents. So this means there are no VOCs, there's no solvents. Whereas the PVDF liquid coatings can be up to 80% solvent at the time these products are applied to the metallic substrate. So 80% of what you've got in that solution is basically going up and being burned. The heat is recycled and used again, but the CO2 is emitted from burning the solvent. The FEVE materials have a lower curing temperature, whereas PVDF does require about 40 degrees C higher operating temperature. And with the FEVE powder coating, you can use a range of gloss, whereas with the PVDF coating, you're limited to a mid-range gloss. You don't have that flexibility that you do with the FEVE coatings. So in summary, what these do for you is you can meet the AMA 2605 10-year weatherability standard. The application efficiency of these materials can exceed 90%. That means there's no waste or very little waste product there. Less damage during installation, no solvents or VOCs. You can incorporate metallic pigments into these coatings with outstanding weatherability. And you have a good single coat formulation that you can use. So where are these used in architectural? Well, they're used as coatings on aluminum windows, on curtain wall, mainly aluminum extrusions for those two applications. They're also used in what I guess I would call architectural elements. These would be things like railings for apartment buildings, flagpoles. They've been used on stadium seating and light poles as well. There's a whole range of applications that these powder coatings can be used in. I wanted to talk a little bit about the carbon footprint of FEVE versus the PVDF liquid. You can see here what we looked at were 4 different formulations, and the main difference here between the FEVE 1 and 2 is transfer efficiency. And the same thing with the PVDF 1 and 2, the difference is going to be the transfer efficiency. Again, these are the most likely, FEVE 1 and PVDF are the most likely that you're going to run into. And what you see when you look at kilograms of CO2 per square meter, you can see the paint itself contributes a certain amount of CO2. That's the manufacturing of the paint and the raw materials. In the case of the powder coating and PVDF, the application process contributes to carbon footprint, where the FEVE shines is there is no solvent incineration step because these are 100% solids with no solvents in there. It does not require that solvent incineration. So even in the worst case scenario, the FEVE coating is about 25%, gives about a 25% reduction over the PVDF one, and about a 50% reduction when you consider the ideal application for both coatings. Just a couple of structures that are coated with the FEVE powder coatings, 35 Hudson Yards and 55 Hudson Yards. The curtain wall are coated with the FEVE materials. The tower at PNC Plaza, this is in Pittsburgh. There are elements on there that are coated with the FEVE. 111th, 57th building, again, the curtain wall, and the same with the Vantage Tower. I think this is in Jersey City, so right across the river. So that's it. Quick and painless.
Thank you, Winn, for the presentation. So we're coming to our panel discussion. I'm sure this is a hot topic for a lot of us working on various projects right now as far as how to resolve the bird-friendly Local Law 15. So with that, I'm going to introduce our moderator, Christoph Tim, from Principal at SOM.
Christoph. Christoph will introduce his panelists. As he introduces them, you all can come on stage one by one. Can I have the screen live, please? Next, back, point.
Okay. Next.
Can we? Yeah.
Yeah.
So you can call your panelists.
Yeah. No. I think everyone on the panel can just step up right here, get going right away. Good afternoon, everyone. Thank you very much for coming, for your interest in this very important panel, I think. No harm, no foul, bird-friendly glass, Local Law 15. I have a great pleasure here to introduce my panelists. We have Christine Shepard. On your right here, she is the director of the Glass Collisions Program at the American Bird Conservancy. We have Stefan, director of sustainability at Enid Architects. We have Sarah Karen, design specialist at Turner Construction. I'm good. And then we have Danielle Tyson just being wired up right now and coming in a minute or a second. And so this panel is a half hour long, and I think we have a lot to discuss. And if there's a real urgency from anyone in the audience, I think the best would be if you approach us after the session, and then we can talk about specific questions. But in the meantime, let's get going here with the questions to the panelists. And I thought the first question goes to you, Christine, because we know you as one of the real an authority here on this issue, and you've worked on bird mitigation measures for buildings for a long time. And maybe you can give us an overview why we are doing this, why local law exists, and maybe you can frame this discussion a little bit.
I mean, there we go. For me, Local Law 15 is really the culmination of about 15 years worth of work. The thing that people seem to want to know the most is, are we just a bunch of bunny huggers, or is there a good reason that we're making these design decisions and using these strange materials sometimes? And the fact is, yes, the bird populations in the world are in a state of rapid decline. Bird collisions aren't the only problem that they have, but just in the US every year, 1 billion birds are killed by collisions with glass. And what do these birds do? Well, they eat the mosquitoes that give you West Nile virus and malaria. They contribute billions in agricultural services. When California burns to the ground, they bring in seeds that make habitat grow again. They pollinate plants. So even though we don't see them working for us every day, they are out there doing things that make it possible for us to lead our lives. And I think that there are many beautiful bird-friendly buildings. And I think that all of you will be participating in building more of them.
So there's some real reasons beyond like just having beautiful birds die. There's some real scientific evidence.
Absolutely.
That they benefit the environment in a much broader way. Stefan, you're an architect, and you deal with Local Law 15 probably on a regular basis, daily basis maybe. And I was wondering if you could give a little bit of an overview of what this law says and what it requires us to do with our buildings.
Yeah. First of all, as an architect, the perspective that Chris just provided is something that I think is probably at the heart of why we are all in this room. We are building an environment, a built environment that also addresses nature. We're bringing nature into our cities. We know that it's healthy. We've learned that in spades over the past 2 years. And so what that means is that we're also bringing more and more birds into these environments. And so this question arose early in our experience, sort of the hard way, right? Some lessons are learned the hard way. Somebody in our office really understood what the impact of a glass building has when you're building near a habitat like Central Park. And took that home and said, look, there has to be a way to address this. This is one of many things that architects need to be able to visualize better and understand almost as a material so they can begin to shape better results. So the conversations that I have on a daily basis are really to sort of explain how to interpret Local Law 15, how to understand it as a framework that illustrates load that your building is experiencing in terms of where bird collisions can occur and where they occur in high-risk situations. And I communicate that visually, and thank you. Good timing. There's a wonderful diagram behind me, which I think is based on some of the supporting materials that are attached to Local Law 15. And it's pretty self-evident here that there's a lower portion of the building that basically is parallel to the mature tree heights in New York City. That's the driver there. And then there are also adjacencies to green roofs that are critical and balconies. And I just want to say that of all of the glass square footage in the environment that I see, and I haven't asked you this question, but I think glass railings probably have the highest intensity of collisions. And that's also covered by the law, which everyone needs to realize.
And I put this little, the cover here of this document from New York City in here for the audience to understand. So there's local law that you can look up, Local Law 15, but there's also this great document that explains it a little bit further. And so please, if you're really interested, download it and go through it, and it'll give you a lot of answers to your questions that you probably have. Danielle, as a glass whisperer to architects and everybody in the facade industry, could you please talk about some of the solutions that the glass industry has come up and how we can address this local law.
So from the perspective of a glass manufacturer, there's a lot to consider. First, glass is a human's connection with nature, and it's also threatens to birds. So we want to be able to have transparency. So that's really important. And there's a lot to consider from a manufacturer's perspective, as well as from a design perspective. Compliance with energy code, compliance with bird friendly, how the glass looks, the aesthetics of the project overall, the cost, and then the manufacturing and design complexity. And what I mean by that is, does the framing system that you've selected in your design work in conjunction with the bird-friendly solution that you've selected? So the most available glass-specific products for this are, I want to be able to...
Yeah, I can...
So there are three main solutions here, and Guardian work with all three of them, produce all three. Bird-friendly fritted glass would be probably the most well-known, a pattern on typically the number 2 surface of an IGU. And then bird first etch, or an etch pattern on the number 1 surface, allowing for the low-E coating to stay on your number 2 surface. And then finally, bird first UV, or a UV reflective coating applied to the number 1 surface in our case, which allows for the birds to understand that there is a pattern on the glass with much significantly reduced visibility from the human perspective. So allowing for clarity and that connection without interruption from the UV solution.
So basically the birds see it, but the humans don't see it.
Correct.
Okay. And you brought some pictures also of some recent projects that you've done.
That's
with
right.
your glass, and you can go through those.
So the top 2 exterior and interior view of the bird first etch solution. So here we have the etch on the number 1 surface, like I mentioned, and from the exterior we have it really blending into that facade. From the interior, depending on what we're looking at through the window, it's more visible in some areas and less so in others. Below we have the bird first UV, exterior again on the left, and the picture on the right is the interior view out, also looking at the exterior of the building. So you could see that the deterrent, the pattern, is much less visible and pretty much not visible at all in those completed images.
Okay. Sarah, as you represent the builder side here on this panel, you also brought some case studies, and I was wondering whether you can talk about those and maybe share some of your stories about these projects.
Yeah, sure. So the building that we see here, this is 181 Mercer. It's a tower in Manhattan that is built as an addition to the NYU campus. And as you can see, the curtain wall is used extensively. Now, this was designed by Karen Timberlake before Local Law 15. So the pattern was developed along the guidelines of bird-friendly design by ABC. However, it does not comply with Local Law 15. It's still a very proactive attempt at changing glass. And what they're doing in this example is they've applied a ceramic frit that covers 5% on inside the surface number 2 of the IGU and combined it with a low-E coating. So this is one application that we're seeing here in New York.
And another one that I brought here is one that probably most of you are familiar with, the Javits Center. Maybe you can talk about that a little bit too, what you guys did there.
Yeah, so we have to say that everyone knows the Javits. I think the main renovation that was done in 2013, that was a complete game changer. They replaced the entire glass with bird-friendly glass that was not done by Turner. What we did was the expansion with TVS, and that portion of the building has a huge glass atrium. And it was a bit of a challenge because we were trying to, with the design team, match the new glazing system that was substantially different because it used glass fins with the existing building. And so we had to go through a lot of VMUs and visual mock-ups to make sure that the two matched. But it was, again, another successful project, and this is, in fact, complying with local law 15 because it uses a 25% coverage frit with low E-coating.
And from what we see now, is a big difference to what it was before in terms of bird fatalities?
Yes, and I believe that, I'm sure Christine can talk more about it, that's in part because of the frit, but also because they've replaced part of a facade with metal panels, which we all know is a much better solution against bird collisions.
And this replacement of metal panels, was that just arbitrary, or was it based upon some analyses or findings?
I believe that was done specifically for bird collisions.
Right, there were 3 little street trees that apparently were causing about 80% of the collisions on that building. So they just made the wall so it couldn't reflect.
So the solution sometimes is not in the glass, sometimes it is in replacing the glass.
It's very pretty though.
Local Law 15 gives some specific performance criteria for the glass so that birds understand that what is ahead of them is actually a glass facade and needs to be avoided. It's called the threat factor. And how is this threat factor established? And maybe Stefan, you can talk about this. And
sure. Well, that's right. We're curious as architects, and that's a term that we also need to understand so that we can begin to sort of see how we can manipulate results. And so the threat factor is similar to any other performance index that you might get on a piece of glass or a glass assembly, whether it has to do with solar peak gate coefficients or U values. It sort of functions in a similar way, and it's based upon what's called a binary choice protocol. Imagine you're a bird, you're placed into an environment that you want to escape from, and you're given 2 choices, one on the left and one on the right in this case. And these are photos that are taken from the test tunnel that the American Bird Conservancy has been using to develop these test results, and this is what Chris has been leading. I hope it's all right for me to speak of this because this is a fascinating little piece of architecture in itself. And it tests proposed samples against a standardized test methodology and basically gives you an index that you can use as you're evaluating some design solutions. One thing to sort of understand is that this is no guarantee about actual performance in the field. There's no way to replicate every condition that you're going to have that captures all the possible scenarios of assemblies and environments that you might be in, not to mention lighting conditions, seasonal, et cetera. But it gives you a very good indicator for what is recognizable by those birds most at risk, namely the migratory birds. And what I love about this installation and others like it are that they are placed in high-density migratory paths, and so you get to watch, as I did, bird handlers capture and tag birds. You get to see, maybe 100 different species flying through, all of which are used, except for those, there are certain that are excluded, certain birds, or if they're stressed. You really get to experience that flow, that migratory flow that's mostly elusive to us urban dwellers.
So twice a year when the birds show up on the way, somebody captures them and somebody puts them in the tunnel. And
put them in the tunnel, and sometimes one of them says, "Oh, not this again," and so and then they fly on.
So it's a bird mix, you said that already. And so for one product, how many times do you run the test like this? Is this like one time only, or is it multiple tests, or how does it work?
So it's 100 flights that give you a level of confidence, and now I would have to rely on Chris to sort of provide the scientific basis for that type of testing. But generally speaking, you want to fly at least 80 birds, up to 100 to get a score that can be compared to other scores using the same protocol.
So I think New York City, generally, I think there's varying criteria for what the local law prescribes. 26, I think, is the standard. And
25.
25, I'm sorry.
Yes.
25. And so, Danielle, the glass that you were just talking about earlier, are those glass types typically meeting these criteria?
So that's what we aim for, and that's one of our challenges. Is New York has this legislation, and there are other cities. So as a company who operates in North America, trying to make sure that we've checked as many boxes as we can for that. But New York being sort of the benchmark, the standard with that threat factor. So a lot of the options that I showed, maybe not all of the patterns, but the options that I showed do meet the required threat factor. And I think one of the misconceptions in terms of solutions is the more, and Christine, I think you can sort of back this up, that the more coverage, say it be in a an etch or a frit does not equal better performance necessarily. It's really about creating contrast so the birds are able to discern that it's a solid and not something they can fly through.
That's absolutely right. The birds don't care what the pattern looks like. They're interested in the spaces between the elements of the pattern and whether or not they believe that their bodies will fit through those spaces.
I was just going to add on to that I think initially there was a concern that there was going to be densely covered patterns on the top. So just keep that in mind and work with the manufacturers, check in and see what options have been tested, what do score a 25, that you may be surprised at how little coverage can still be effective.
They're effective patterns that cover 1% of the surface of the glass.
That's right.
I mean, testing sounds great for a big project, but I was wondering if there's also other compliance paths besides testing for smaller projects. Maybe Christine, you can talk about this.
Well, we've been very concerned that the requirements of Local Law 15 not inhibit construction projects. That's the last thing in the world we want. And one of the things that we've done is create an evaluation group. If somebody is proposing a glass that's very similar to something that's been tested, then this group is able to take a look at a sample. We actually throw reflections on it up in my attic and see how the glass performs. And then we assign a conservative threat factor. So what we're really concerned with when we do this is whether or not the glass would have a threat factor of 25 or less. If we believe that it would have a threat factor of 25 or less, it gets a 25. If the manufacturer thinks that it really would get a 17 in a test, then we take it to the ton.
So it's kind of like an engineering judgment based on some experts that...
We have a bunch of biologists and a bunch of architects so that nobody can get carried away.
But you're right. I mean, that's a term of art in a way, the engineering judgment. That's sort of how that functions. And that evaluation is placed on the table that's referenced in the law.
But it doesn't make sense, for 8 companies to have to test the same thing.
Right. And then there's also some, what I'd call like off-the-shelf material that people can look at. You have a database on your website. Maybe you can talk about this for a second.
Right. Everything that we've tested and scored is listed on our website. You can go to, that's the direct link. You can go to birdsmartglass.org if you want to see all of the materials we have for collisions. If you do that and hit the menu button, you can go to the database, you can go to the section on legislation, ordinances, and code, and on that page is a link to resources for Local Law 15. So we try to explain everything. There's a long essay on what a threat factor is if you really want to know, sort of the basics. We've tried to answer as many questions, especially the common questions that we get, and put them there in writing.
So the bird deterrence is one performance criteria of the glass, but of course there's others, solar heat gain, U value, and so we on a typical IGU we only have 4 surfaces. Is there any known issues of where those coatings can go or the frits that you want to talk about, and how these different performance criteria influence themselves?
The answer is yes.
Yeah.
and all of us actually relate to that question in different ways, but maybe Chris could begin.
We don't have a lot of information on how well frits perform on surface 3. It's obvious from looking at them that they're less visible than they would be if they were on surface 2. And you can't just say surface 3 because the spacing in the IGU can be different, and that has an impact on visibility too. So right now we can't say much about materials that have their patterns on surface 3.
Yeah, so the way I think about it is, first of all, when I look at a glazing assembly in section, I see it as a stack of technical sort of layers, but if you're looking at it visually, I call it a phenomena stack, and certain things in the background can override things in the foreground, and so it's really, you have to think of it as the impression stack as you're approaching this assembly, and that's where reflections and contrast values come into play, background conditions, so many things come into play. So you really have to think about this carefully.
Yeah, I mean, the critical thing is that the reflection on surface 1 doesn't obliterate the view of what's behind it.
Right.
But if all things were equal, where would you like to have the deterrence?
That sounds like a leading
Surface
question.
one.
Surface one, yeah. Okay. Talking about commercials for a second here, Sarah. Are there any issues that a specifier should be aware of when specifying this? Any pricing challenges, any schedule issues that you want to talk about that you've learned that should be avoided?
Yeah, so I mean, ceramic fit, we've been applying this to glazing for years and years. There's nothing really difficult with that. The issue is now that we're seeing a lot of proprietary products that are out there, I think there's going to be a challenge when in procurement if things are being specified prescriptively, where we might be inadvertently limiting the number of vendors because we're specifying, a coat on the surface or a specific type of treatment. And so I think it is going to be critical to do the proper market research and understand what products are available before specifying these things.
But generally it is.
But generally, no. I mean, the ceramic fit in itself is not an issue, yeah.
I just wanted to add that to an extent, this is a moving target where new products are being developed and tested all of the time. So once again, I just wanted to reiterate, it's really important to check in with the manufacturer early and often to see if new products have been developed that maybe from an aesthetic perspective you prefer. From a cost perspective, it works better. So really check in early and often as this progresses and starts to expand, where maybe there won't be products that are so proprietary, it'll be more widely available. So it's still new and moving.
Okay. Besides Local Law 15, there's also a lead pilot credit. It's slightly different, but maybe we can talk about the differences between Local Law 15 and this pilot credit.
The pilot credit is going to be permanent as of the beginning of the year. The site subcommittee just voted to put it into the permanent library.
That's great to hear, and maybe
that is great. No, and I've heard that it's been the most popular pilot credit over the years as well. I think people really sort of take this issue to heart and have used it. So what I was describing earlier in terms of our experience with this, it actually led to the development of Pilot Credit 55. We worked with Chris to sort of see, well, what are the conditions that we need to understand as designers and that we can begin to track and measure and even sort of rate glazing assemblies by, and that's what resulted from that effort, which was LEED 55. One driving goal for us at the time was to make sure that it allowed optimum flexibility, and so we created this formula for evaluating a building project and really assessing every square foot based upon its materiality and its threat factor so that we would sort of aim for a building-wide threat factor score. I think of that as a performance-based model if you want to compare it to energy modeling, whereas Local Law 15 is more like a prescriptive approach, and yet I still think of it as a performance-based intention because there are so many different ways in which you can achieve the prescribed threat factor of 25. Back to your point, I think that innovations are occurring constantly, price points are changing constantly, demand is changing, and when you remember where those impact areas are in that building diagram, and as a designer you're beginning to develop an identity for a design proposal, all of these things come together to achieve multiple goals. So I don't think that Local Law 15 impacts creativity at all, and I think LEED may actually evolve to become a bit more, prescriptive in itself, right?
A lot of this is what we're seeing now is actually derived from the pilot credit. When I first started, the advice that biologists like me would give to all of you went something like increase visual noise on the facade, don't use large pieces of glass, don't put something close to a water source. And when we started to try to make a LEED credit out of this, the subcommittee said, well, how big is large? What is visual noise and how far is near? And that was when we realized that we were going to have to come up with something that had objective criteria.
But if I understand this correctly, if you meet the criteria of the pilot point, you're not necessarily complying with Local Law 15.
That's right.
Okay,
that's
so
right.
Okay.
Just they're not related in that sense.
Okay. And do we think that Local Law 15 is evolving in the next years, or is this?
It may. it's not easy, I think, for code in New York City to evolve. To make a change, you almost have to go back to the city council. So I don't think we're going to, whereas with the pilot credit, because it's a pilot, you can make changes relatively easily. That's not the same thing with Local Law 15 of 2020.
So far we've talked about Local Law 15, but I thought maybe we can also, for a few minutes, talk about what we see in other jurisdictions. Is it similar approaches, or yeah, maybe you can talk about this.
Sure. So in working with our team, I've come to see other jurisdictions and what their requirements are, and they're quite different from New York in a lot of cases. Toronto, for example, in 2022 will be requiring not a specific but a first surface deterrent. So, and they're less specific about a certain score, but that's what they're looking for there. So that's the one that I think is a stark contrast to sort of what New York is doing. But it's sort of proving that point that the first surface deterrent is typically most effective.
So the general trend has been that the regulations, of which there's many at local and state and national levels, have all been shifting from the qualitative to the quantitative to answer the two questions. What do you mean and how do you know when you get there? That's how a law becomes a law, because it's enforceable, because it explains how. Canada developed an interesting standard which is the most prescriptive that I'm aware of. They prescribe a pattern. They say this is it, this is a 2x2 surface 1 approach, boom, that's the criteria. So that's a much more, I think, restrictive approach than Local Law 15 is, certainly.
It's funny because it's prescriptive, but then they're limiting the area to like 50 feet instead of 75. So
yes, that's true too. That's right.
Yeah.
Coming back one more time to New York, to the Local Law 15. In our office, there was a little bit of confusion about there's a multiple paths to compliance in the law, and one of them is called ASTM, like the pending ASTM. And I thought maybe it's a good moment here to clarify what this means. I know you guys know about it. Maybe Christine or Stefan can talk about it.
We've been co-chairing an effort of ASTM members, which probably includes all of you, over several years, because one thing we're trying to do is gain consensus. And even though the ASTM process is not dependent upon 100% consensus, I think that in fairness, we're trying to really pay attention to what everybody's concerns are, and this includes the latest developments in the infrared, which require different sort of verification methods. There is a standard that is in draft form, I think it's version 8 now, that is getting very close to getting voted in. And what it does, though, is it basically just codifies the binary test protocol that's used in the tunnel that ABC has been using for many, many years. So it's not something new, it's just written as a third-party verification method through ASTM, so that it can be included as a reference in our national building laws.
I think that was good to clarify.
Yes.
And we're running a little bit ahead of time, so I think we have time to maybe take one question if there is any in the audience.
Any questions? Can I get a mic? Sorry, if you don't mind, can I get a mic?
Christine, I remember when we worked together, you said that the tunnel test was not very effective at testing textures versus frit patterns. It was more effective with patterns that are kind of imprinted on the glass rather than patterns that break up reflections. Is that still the case?
The tunnel was actually, the tunnel test was invented in Austria because they'd installed a lot of highway noise barriers that were killing lots and lots of birds. So the tunnel itself was originally intended to test freestanding materials. And we adapted it so that it can test materials that are applied to a facade. But as I said earlier, what's important to the birds is the spaces. And the tunnel is not necessarily the appropriate test for an all-over texture. On the other hand, there's room for common sense in this whole rating business. We've added things like concrete and brick to the database because, I don't have to put that in the tunnel to know that birds are going to avoid it. So there are textured materials. We've put in different kinds of polished metals. We're trying to put everything into that database, including external sunshades, that we can, and not everything can or should be tested in the tunnel to get a threat rating.
Right. So you said that the local law says that the factor to decide whether the material is bird friendly or not is 25, which I'm assuming is 25 birds or less will collide on the glass out of 100. Is that right?
That's right. Yeah, 75 avoided.
75 avoided. What is the base case if it was not bird friendly out of 100 birds, and if you just say go into a normal regular glass, how many would collide otherwise?
When you put birds in the tunnel and you're not testing something, you expect 50% of the birds to fly to the left and 50% to fly to the right. So birds are not handed in a situation where they're coming out of a space like that. So if you got what essentially would be a threat factor of 50, that would mean no effect whatsoever.
It would be 50 collisions and 50 non-collisions.
If you had 50 collisions and 50 non-collisions, that would be different. That would really be a threat factor of 25.
Zero. I mean, it'd be very low. I'm sorry,
Yeah,
did you say 50 collisions or 50 avoidance? 50 collisions? Yeah. And 0 avoidance? Okay. That's what you just posited? Is that right? Did I get that?
I mean, that's essentially a threat factor of 100. Basically, we won't test something that we don't think
I'm
has
not
a
still
chance
clear.
to get a
In terms
score.
of the base case, what are we looking at? Say there is a glass in the tunnel test which has no pattern whatsoever. What are we looking at? Would all the 100 birds collide because there's no obstruction and they're not viewing anything?
Yeah, 50 would presumably go to the left, 50 would go to the right.
And
yeah, right.
And that's what we see. When we start the tunnel every season, we run at least 100 birds with 2 pieces of plain glass. And we expect to see that 50-50, no effect. If we don't see that, we know there's something wrong and we have to fiddle around with it until we
It's
get
actually
the
how they
right
aim
balance.
the mirrors. They have to calibrate the tunnel at the beginning of every season to make sure it's functioning, and so they actually do that 50-50 test. And then they start putting in samples.
I'm Hisham from Saint-Gobain Glass. I just want to know how the local law 115 is enforced.
Like anything else in the building code?
Well, that's a great question. That was my question too. So the guidance document gets into this, and it's, in fact, it shows examples like this in terms of how you might choose to document, your compliance to demonstrate that you're meeting the compliance. If you're familiar with our energy compliance submissions, when it comes to our facades, it gets quite, elaborate, not maybe more than what's asked for. But I certainly have an approach which will look very similar to an EN series set of drawings, and other firms may have different approaches. I don't think the law is looking for that level of articulation. But as far as, I think you're saying enforcement, I don't know.
This topic can go on and on, as Christoph said. We can talk this over coffee because we need to complete this session. Christoph, closing comments?
Yeah, I would like to thank my panelists here. I think this was interesting, and just like Ahad said, we can continue outside. There's a lot more to be discussed, but thank you very much for your interest.
Thank you all. Can I ask Jan to be on stage, and can we have a photo session with the panelists? So this track is ended a bit earlier than the other 2 tracks, so I think you guys have a longer break. The other 2 tracks will take another 20 minutes to finish. So you guys can interact with the panelists. We'll take a photo, and all of them are here. Jan, please. Can I get the photographer on stage, please?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. 1, 2, 3. Okay. 1, 2. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2. Now if they play something. Want to talk here? Two, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1. Are you able to play something from there, DJ? Josh, you hear me down there? Not yet. What do you mean? Not yet. Go ahead, podium.
All right, speaking on the lectern, speaking at the podium, 1, 2, 3, 4, 5. Tapping on this one.
Okay, I hear you.
Tapping on this one. Tapping. Testing 1, 2, 3, 4, 5.
Got you.
And we also, this is a presenter over here coming up, so he maybe need to be much.
1, 2, 3, 4, 5, 6. I don't hear this side. 7, 8, 9, 10, 11, 12. 1, 2, 3.
Stand by for PC audio.
Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Okay, PC audio should be coming through. Very good, we got it. We kill it.
Okay, that was PC audio. Thank you. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. 1, 2. 1, 2, 3, 4, 5, 6, 7. Why? 1, 2, 3, 4. 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4. 1, 2, 3, 4, 5. One, two. 1, 2. One, no, 1, 2. Yeah, 1, 2, 3, 4, 5, 6. Hold on a second. 7, 8, 9, 10, 11, 12. 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, yeah, 9, nope, raise it more, 10. 1, 2. Oh, it's, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll take care of that.
Test. 1, wait, I hear it. That was it. 1, 2, 3, 4, okay. 1, we good? Yeah, thank you. It was on this side, thank you.
start the session. Can I request those outside the hall to please make your way inside? Last session, we'll wrap this up and have the post-event networking, please. We are starting the session anyways due to paucity of time. Attila, please.
So our next presenters, for those guys that are more interested in facades than in bricks, is actually a German engineering firm that has come up with a facade Local Law 97 renovation or retrofitting project that we will face in the next couple of years. So, a couple of years. Given the delays, unfortunately, we lost Steve, but we have Stefan here still available. So, without any further ado, let me introduce to you Stefan Goebel of Priedemann here in the US.
Thank you very much, Attila. You need the mic on? Check, check. Is it on?
I guess it is.
Is this on?
Check, check, check. No, we go. Okay. Yeah, I apologize. Steve had to leave. He had to head to the airport to go back to Germany. But I'm the young one, and I have to do the legwork, so I'll get to do this. Thanks, everyone, for staying for this later session this evening. But I think it's an exciting one. I'm Stefan Goebel. I'm in charge for business development within Priedemann in the United States. And both topics, Local Law 97 and Local Law 15, are really dear to me. I have really been inspired 2 years ago when Christoph Timm, and there was a panel around it, first talked about Local Law 97. And he had it printed out, he picked it up, and he asked, had anyone heard about it? And no one really raised their hand. So I started studying it, and I learned really, okay, this is something is changing in this market. Same with Local Law 15. I worked with helped the DOB come up with guidelines on how the Local Law 15 could be realized, established. So today we'll talk about a facade concept called the active cavity transitioning facade that hopefully helps cut emissions. And to me, as a passive house consulting, having emissions limits or energy use limits is really not so new of a concept. And I'll also talk a little bit about Local Law 15. Very quickly, Priedemann is headquartered in Germany, present globally, about 157 of us, solely focusing on the facade envelope. So facade consultancy and engineering. We've been in business since 1993. Just a couple of projects. Obviously, we've done a lot of work in Germany, and code had developed in Germany long ago, so we're used to high energy efficient facades. We're used to high-rise buildings, a lot of work in the Middle East, and we've done work in North America as well. But what I think is unique about it is, so we're supporting the architectural community and developers during the design stages, but this part down here is more important, working with the general contractors and the fabricators particularly. We collaborate with industry and always have the user in mind. But particularly the fabricator know-how in our firm is very deep. A lot of our consultants have worked with facade fabricators before, and I think that bringing that knowledge into an early design stage is going to be crucial, and then also following through during the execution of projects to make sure that the buildings that are modeled are actually performing as they've been designed is extremely important with Local Law 97. So if we want to be carbon neutral by 2050, if you want to meet Local Law 97, you all know this, we can't have this. We have to have a continuous flow throughout from design all the way to the execution. And when I heard about this the first time, I really love this. And you all can read, but as a class, being in a glass industry and aluminum industry, that statement definitely shook our industry. But I do think that as a passive consultant, again, I was really happy that we started having this conversation. In the same time, Local Law 15. It's extremely important to consider the impact buildings have on our ecological system. But I do think that we don't have to ban these kind of buildings. There are strategies to work with high window to wall ratios. And I want to show you one case study. It's the Festo Automation Center that we've realized in Erleen in Germany. Festo is known for its innovation, and I wanted this building to be DGNB Platinum certified, similar to LEED Platinum. But you see they wanted a traditional glass cube for their headquarters. And the window-to-wall ratios are challenging. The heat gains can be challenging there. So we had to overcome this, and this was part of a consultancy process to look at different facade systems. And I'll come back to that in a second, what we looked at. But essentially what the outcome was the active cavity transitioning facade, a standard unitized curtain wall system that is tightly integrated with this pliant for glare protection, but it creates a buffer zone. And it exhausts the air here on the upper side of the unitized curtain wall. That air gets up to about 80 to 90 Fahrenheit, and that gap is only about 6 inch deep. So once the solar radiation hits the facade, that air is heated up, it's exhausted, it can be used through a heat exchanger, or it can just be exhausted, but it's not getting into the building. So the cooling load in the summer that we have to supply can be a higher temperature. So we're shaving off those peak cooling loads. And shaving off the peak cooling loads is crucial if we want to bring the energy use and the emissions down. A short video here. It's a typical high-rise office, unitized curtain wall. Apologize, it's pretty loud. But what we're looking at right now, the air in this case is supplied in the center of the room. We have the diffuse daylighting, so the sun is not hitting the facade. It's exhausted through that gap within the facade, and the air is heating up. It's exhausted, perhaps be used through a heat exchanger. And then as soon as this part of the orientation of the building is exposed by direct sunlight, we're moving it down. And you can see the blinds that were developed to be used in this system, and they're translucent so that we maintain views and daylight, but we're shaving off the cooling loads in this particular case. And what we're really looking at as well with New York City, saving space. So we're comparing this during this consultancy approach to a double skin facade, which uses a lot more space and lots of rentable floor space, as well as, this is moving slower than usually, closed cavity facade, and we looked at an internal ventilated facade as well. All of those not as slim as the unitized, the active cavity transitioning facade. And moving on. So we've measured this facade with the Fraunhofer Institute in Germany, and actually the Festo project we looked at twin rooms. So we had these rooms down here. Both of them were designed with the pliant that was designed to be used with the active facade. One was only ventilated. So the one that was ventilated, we shaved off the cooling loads by about 25%. So this particular case, we didn't look at the winter scenario, so we could use this heat gain for heating as well, so this would be another case. And what we looked at as well, and this was significant, so we see here the solar heat gain coefficient in this one room is about 21% with the pliant down. As soon as we start moving the air through at about, we see here about 10 cubic meter per hour, we are cutting the solar heat gain coefficient in half, which really makes a big difference. So with this project, it had really been in operation since 2015. The DGNB Platinum certification was achieved as well, so they're quite happy with it. It made its way into low-rise, where the architect here wanted to achieve a continuous appearance throughout the facade. Was applied slightly different. A similar concept, however, the pliant is moved down all the way. It's static, it's sitting there, and it's actually exhausting the air through a perforation of about 5% that we have continuously within this pliant. And this one was measured as well with the Fraunhofer Institute. And so we looked at the operational room temperature. And so for this office building here, so these are kind of the boundary conditions, we only had a couple of set points where we were outside of those conditions. So it performed really well. On the right side, we looked at the continuous daylight automation, which we were at roughly 52% in average, which is a really good value as well. And we're penetrating into the room 8 meters, so about 24 feet. One of the things that we measured as well for comfort, extremely important, because we always need to have the user in mind. So the surface temperature. As you can see on the left side, what we have here is in red is the temperature within the cavity. The solid line is the simulated and the dotted the measured, so they're both pretty close. And the blue lines, both measured and simulated, they're really in the comfort criteria. But more important, on the right side, for comfort criteria, we measured the internal temperature on the screen, and that didn't deviate more than about 7 degrees Fahrenheit to the internal room temperature, which we really want, because otherwise, we have convection happening and we have an uncomfortable feeling right next to the facade. In Berlin, we have a mock-up of this setup looking at the double skin facade, closed cavity, box type, and the act facade. And you can kind of get a feeling for how much heavier these kind of systems are compared to this system. We save about 25.6 inch here instead of comparing it to a double skin facade, which is significant if you think about New York City's square foot values. We looked at different types of facade, and this is what I was mentioning earlier. So we looked at the U value of the act facade compared to double skin, closed cavity, box type, electrochromic, and outer shading. Outer shading always preferable, but it's a problem with winds in high-res buildings, so can't always use those. We looked at the solar heat gain coefficients, and the active cavity transitioning facade was performing almost as well as the external shading, which is significant as well. The internal surface temperature, the act facade was actually outperforming the double skin and the closed cavity and box type facades here too. And one important topic we've talked a lot about, global warming potential, we use a lot less material. So this is a typical system. This can be done with local labor force. This is pretty trivial. I think that's important if you want to make those big changes, that we come up with simple solutions. This has been used at the Ardix Tower in Witten, but more importantly, it had been used in the Eurotower in Frankfurt, where this building, the goal was to bring it up to the latest energy standards. And the idea was to refurbish the facade, tear it down, and upgrade it, different glazing. But the act facade there acted as a plug-and-play system. So the ducting had to be changed, the act facade was added, and it brought that building up to a better energy standard and extended the lifespan of this building, which I think is crucial to mention. So because we gained a lot of knowledge through this, we actually proposed this as Metals in Construction Design Challenge in 2020. So the idea was to bring this 60s building, 63rd Madison Avenue, to a current energy standard. And so it was awarded, the act facade, but it unfortunately wasn't realized. But I do believe that the original statement that the mayor made, I think there's a lot of truth to it. But we do have a lot of old buildings that are really, really inefficient. So there's ways to design buildings with high window-to-wall ratios that can be energy efficient as well. And as always, there's a team required to do this. We work closely with Transsolar, with Chico, Varima, and the Fraunhofer Institute. There's additional research going on right now on the flow, upward, downward, through the screen. So we're still measuring. And then also we're looking at different textiles that we can use. And at this point, we're looking at Venetian blinds, we're looking at curtains, but we're also looking at applying patterns to these blinds. And that might be beneficial for mitigating bird collisions. Brings me to the next topic. So has any one of you seen a bird collide with windows? Raise your hand. Has anyone seen a person walk in class? Anyone walked into class? I've done that. So it's painful, but birds actually approach glass not at about 5 miles an hour, about 30 miles an hour. So it's deadly for them. It's estimated that about 1 billion birds die a year in North America because of bird-window collisions. And they simply can't see this reflection, or actually they're fooled by the reflection. They see the sky, the trees in this left scenario. So high reflective glass is an issue. I'm going to move on. This is awful, I know. But it also, the transparency of the glass can be an issue in these corner situations. And there was a session on it earlier. So for any one of you who has not been there, quick follow-up. New York City has introduced the strictest law on bird-friendly material requirements. So essentially any building since January 10th this year that had not been permitted, the first 75 feet have to use bird-friendly glass. Go back. 12 feet above green roof, and any glass corners and railings have to use bird-friendly glass. So this is a big change. And I want you to take that back. That's an important point, the material threat factor. So what do we need to specify, and what do we need to use to comply to this law? The material threat factor at 25 is written in the law, and one way to get there is by the American Bird Conservancy's tunnel test. Dr. Chris Shepard's still here. She's left, unfortunately, but so she's worked on this for now over 20 years, and essentially she's created this test tunnel. It's a 30-foot flight tunnel, dark on the inside. They catch birds, release them one by one in the tunnel. They want to get out of the tunnel. There's a clear glass pane, a test glass pane, a bird-friendly glass pane, and they're trying to understand how many birds out of 100 are avoiding this bird-friendly glass. If more than 70, so let's say 70, the inverse of it is 25. That is the material threat factor. That's what you'll be hearing a lot going forward. Solutions, there's certain material, like a brick wall. Birds can see that, right? They're not going to fly into it. There's certain markings that we can use that birds will see. So essentially here, we see horizontal lines that need to be spaced further than 2 inch apart, or vertical 4 inch. So that would work. There's interesting products out there right now if we want to maintain views. I apologize, the quality here. A manufacturer out of Germany, Arnold Glass, has actually invented a transparent UV reflective bird protection glass called Onolux. There's no other manufacturers like Guardian with the Bird First, Walker, and many are coming. So there's other solutions out there to mitigate collisions. I want to trigger, I think this might be an idea as well. So we thought about the active cavity transitioning facade, and why do we use highly reflective coatings in buildings? To mitigate heat gain. Where do we experience a lot of heat gain? On the south-southeast, right? So they become highly reflective because we want to reflect the solar radiation. This visible light goes down. It's not so great for comfort. But what happens on the north facade? There's barely any direct sunlight. So what if we are not really concerned about that heat gain as much on that orientation? What if we can introduce an element that essentially exhausts the air or utilizes it? We don't need those highly reflective coatings. And if we, at that point, we already reduce the risk of bird collisions, and if we introduce some kind of markings on those blinds that come down at certain times of the day, let's say the early mornings, the late afternoons, or the building might experience collisions during the day, so the building management program could be programmed to move them down at certain times of the day. So I do think we need to think outside of the box to make sure that we can build cost effectively and also mitigate those risks, actually address the issue. An example here before I finish up, visual markings, they're not that bad actually. You know, some can be very subtle. And then there's another example here by Any Architects. It's just one of the bigger applications of bird-friendly glass in 2000. This was 2015, so one of the early bird-friendly projects. And with this, I want to thank you for your time, for your attention, and yeah, I hope to get a chance to talk to you later. Thank you. Thank you.
Well, we are approaching the last session. It is an interesting topic. It is about precast, especially in the context of what we heard today about the energy efficiency requirements that we will be facing fairly soon here in the city. The combination of precast and high performance window components or facades has always been especially with the means and methods that are being used, an area that created a lot of contention. So you have the precast guy, you have the window guy, you have the caulker, right? And there's three trades that are all pointing fingers at each other when it comes to liabilities and leakages. And I think it is critical and important that we understand, number one, that this is an area that is having a big growth potential. And secondly, that we all need to kind of get to the point of talking to one another, coming up with solutions. You know, something that I've been always thinking about is, why do we really have to caulk? Is there any way of finding an EPDM gasket that we can wrap around the windows? And these are things that individual companies have all know-hows that they can bring together with the consultants on this thing. And this really is an interesting topic that I really would love to see for us as an industry to make some progress. And we have some leaders in this today, which is our last session. And it is a panel discussion with some very, very interesting panelists. So if I may introduce you guys to Silverio Patrici, He's the Vice President at Thornton Tomasetti. He will be leading and moderating this panel, which is titled Designing Architectural Precast Concrete Facade. Please join in with welcoming Silverio.
Yeah, can you hear me? Okay, good. All right.
Should we come up? Oh.
Yeah, yeah.
Okay.
Just introduce them. Yeah. Okay, so this is great. I miss this. I love being back. It's good to see all of you. There are so many familiar faces, a lot of handshaking and hugs. I missed it a lot. So today I'm here with three amazing professionals. We have Guy Tremblay. He's Vice President for Business Development and Pre-Construction at BPDL. And then we have Russell Crader. Russ is an Associate Principal at AJ Associates here in New York. And then we have Christine Yoon, and Chris is actually an Associate at OMA here in New York as well. And the topic for today is designing with architectural precast. But you will find out that there is much more than that in this presentation. There is a connector between all the presentations that you will see. It's design, of course. It's also about people. It's about people that work in this industry and make a precast project happen. It's about all the people that are building all the molds that are used for precast panels. The molds themselves are actually pieces of art. And nobody gets to see them because you only see the precast panels on the building. It's about all the people that are laying down the stones and the aggregates in the molds to achieve a certain design intent that you will see in a little bit. Thousands of aggregates, and they are super proud about it, and they select the sizes and the distribution about the aggregates to achieve a vision. It's about the people that develop all the tools that we actually use to simulate certain things, like daylighting, for example, before we even get to mock-ups. And you will see that too in the presentation. And it's about the people that are installing the panels. We're talking about panels that are 20,000, 30,000 pounds, installed overnight at 2, 3, 4 a.m. In the middle of the winter. So it's about design, it's about people. So Guy will actually talk a little bit about fabrication and detailing and sustainability aspects. And then Russell will jump in and he will talk about textures and surfaces and all the things that you can do with colors and aggregates and mixes. And then Chris will actually conclude the presentation talking about geometry and three-dimensional complex shapes and a little bit of mock-ups as well. Now, that said, we'll start. I'm taking care of the history, so it's a little bit boring at the beginning, but it's going to get better after that. So I was doing a little bit of research, to start the presentation and trying to find like a way to describe the evolution of precast, right? And the first thing that I found, it's actually this image and a very interesting article that was talking about the Roman Empire and how Romans were actually using some kind of prefabrication and precasting at very early stages to build some of the most amazing architecture and infrastructure out there. They were using precast element, again, at very early stages, to build tunnels underground and aqueducts. But we don't have real precast until the early 1900s. And the first building was actually a house that was developed by this gentleman, John Brodie, an engineer. And he came up with a design and he actually built a house for this cheap cottages exhibition in the UK. And it was not about architectural precast, it was actually about structural precast. So the structure of the house was prefabricated, and that was the first example. By the way, I was also looking in Wikipedia, and the powerful tool is also telling me that he developed the soccer goal net, which is like kind of cool as well. So that's the image right there if you're wondering why I'm showing that. But then, you know, if you keep moving forward, you get to the 50s and the 60s, and you know, we were presenting and we were trying to prepare the presentation together, and actually I found a slide that Guy put together in his deck, and I was like, I'm going to steal this one, and I'm going to put it at the beginning, because I think this is the perfect description of precast. So precast concrete is the only material that allows architects to fully express their creativeness, like a canvas that an artist would use to paint their masterpiece. It's like the perfect description. And you will see what that means, because there is so much more that goes into precast panel. It seems like a very simple process. We're talking about concrete, but there is so much that goes into it. And it gives you so much freedom and flexibility in your design. And some of the examples that you know, Guy and Russ and Chris will present actually will show you that. And this is my last slide. And you know, like when I came here today, I actually met a bunch of people. One of them is here, and I was super impressed because, you know, Dan actually worked on one of the tallest precast building in New York, and I think in the US, right? 99 Church Street with Ramsa. And then I met Akim as well. I don't know if he's here now, but like, you know, he actually worked on 11th Height with Studio Gang, one of the most complicated three-dimensional geometries here in New York. And there are so many other examples. Like literally there are many projects that are using precast that are already built or they are under construction or they are in design. And there is a change that is happening, and I'm sure you heard a lot about it during the other presentations today. And we're definitely moving a little bit away from the glassy buildings, right? I mean, it used to be all glass. Now it's a combination of glass and other materials. And there are different reasons for that, certainly like sustainability aspects and certainly energy codes that are becoming more stringent. But precast, it's really helping developing a new skyline. These are all projects that are changing New York City, and there could be many more, and there will be many more, and this is happening not only here, but it's happening around the world. So that said, I'm going to leave it up to Guy. Okay.
Merci. So thank you, Silverio. So Silverio and I, you know, we've known each other for, what, 8 to 10 years, working mainly on precast projects. And I really appreciate your introduction, making, you know, a relation between art and precast. Because when you get to know what precast is and means, there's a lot of workmanship involved into fabricating a precast panel. And one of the things that I enjoy the most working here in the city of New York is the mindset of people. Like they can create almost anything with a very few principles. And precast, you know, it's quite simple because it's made of mainly two things. It's made of a paste and a coarse aggregate. So basically, when you want to do you want to play with colors. Well, you can work with the color of the paste, which is basically made of cement, sand, and pigments. And you can also choose an aggregate with a distinct color. So basically here at the bottom you see this is the image of a white paste with a dark aggregate. And just by playing with the finish, you know, we go from white to gray to black. So the second sample is basically a black paste with white aggregates. So if concrete is the paint that we use, you know, the canva for precast will be the molds. And one of the reasons why, you know, we've been successful in the city of New York is because we have good carpenters. And working at wood is not, as Silverio said, does not show up on the building. But if you can have good carpenters working in your companies, you're going to be a good precaster. So it's not much about pouring the concrete, but it's about fabricating molds. And we can make molds out of wood. We can make molds out of rubber or steel. It's all about, repetitions and usage and cost, obviously. More and more, we get aids that help with CNC machines to create three-dimensional shapes. So I attend the talk on just earlier on the new Yale residences given by Kurt, from Robert Stern, and all that cast stone elements were actually fabricated using that single CNC machine here. And all the molds, that were used to do those passageways and chimneys were actually manufactured in this shop. So once you have molds and concrete, well, the only thing you're missing is an architect, someone with creative ideas, right? So precast can become anything. So when I started I started in sales just about 12 years ago in Montreal. That was just after 2008, when the market crashed. So we were doing a lot of businesses in Boston and New York, and we had to diversify our market. So Montreal was basically a market that we left behind, and so we had to work again just to gain on shares. So when I started in sales, basically I told myself that any building could be precast. And this is the Tour des Canadiens. So this is basically just next, it's a tower next to where the Canadiens of Montreal plays hockey. We did the bleachers and the stadium back in the 90s. And when I got called on this building, the architects were looking for pavers and benches, right? And I saw the tower, which was all designed using curtain wall. And they had a lot of issues with their budget. And the first 10-story of the building is actually a parking garage. So I said, well, we have a solution for your parking garage. We could use sandwich panel. So you have an outside finish, an inside finish, insulated, very efficient. So they bought into the idea of changing the design to get this podium made of sandwich precast panels. So once we got, they got to know us, I told them, so why not do the entire tower with precast, right? But to move forward with the whole tower, in my mind, we had to step ahead, and we had to integrate the windows into our panels. So that's basically what we did. So we teamed up with a window manufacturer from Montreal, and we installed all those windows into our precast panels. So this is some pictures of different projects, pictures of, and you see basically the operations. So if you compare what it means to install the windows on site and what it means to install it in the precast panels, there's a lot of differences. And mainly in the quality and the waterproofing, because you're basically working in the best possible conditions. It's heated. You can prep your surfaces, so you get really high quality out of it. And on top of that, well, you don't have to use a full day of hoisting to bring your windows to the job site. And when we deliver precast panels, since they're already glazed, your building is enclosed. So we become, that way though, we become fully responsible of the entire building enclosure. So after 2 years of doing sales in Montreal, the economy was back on in New York, so I got sent to the city, and I got hooked pretty quick, to all those big projects. And but working in New York for me meant doing the commute every week, flying back and forth from Montreal to New York City, and I've done it for close to 10 years now. But the reason why I'm still here today, it's not the project, it's not either the beauty of those of the city, but it's the people. So what's here we see Christine, Russell, and Silverio. I think Silverio is like 22 on this picture.
So basically what's unique about New York is when, well, what I like doing when I go to a meeting is I usually ask people where they're from, because I always get the same answers. Like most of the people are not from the city. And, but they have this in common, is they made a choice, right, to come to New York City because they were highly motivated. They were they were great professionals, and they want to make a difference. And in my mind, precast is actually a material that allows people like engineers and architects to be creative. So this is a building on 28th Street designed by DXA. DXA studio on 32nd Street and 5th Avenue. I have to say, you know, with all the trips that I did from Montreal and New York, I think I spent like a year and a half stopping by their office working on this project, because, you know, the first thing that I saw of this building was actually renderings. And when you see this geometry, the first thing, you know, as a precasters, the first thing that comes in your mind is where are the precast joints, you know? So how are we going to build this with no joints? So we basically worked with the architects to find a solutions where joints are hidden, you know, within the thickness of the precast panels. So if you look on the picture, that's actually one of the panels that was mounted on the structure. You see that the windows are already pre-glazed. So only half of that panel is exposed, and the other half is hidden on the panel on the side or on the panel on the top. And that's basically how we created this facade, you know, with the ideas of those architects. And the first time that I saw this building was actually just 2 months ago, and I was really amazed, you know, by the feel that you get when you see it. So if you want to walk, you know, towards 28th Street, it's just, 3 kilometers away? So another of my favorite project is actually 11 Oit in Brooklyn. So 11 Oit was designed by Studio Gang. And the main person behind this design, in my mind, is Arthur Liu. I don't know if you met Arthur Liu. Now is the director of design at Studio Gang. And this building is all up, but right now, you know, this is probably one of the most complex precast jobs ever done. When you looked at the geometry of the panel, the curve, that organic curve that goes on, you know, the horizontal plane. And there's a little story, because when we bid on the job and we got awarded, this is a building, you know, the owner is Tishman Spire. It was built by Triton in Plaza. And we were only committed to have one curve, you know, on the horizontal plane. And then they came with the idea of adding a second curve because it was going to make the building look better. But we already had the contract, you know, to make the precast panels. And the reason why, you know, that second curve got added is because Arthur is a true passionate architect. And he sold the idea to me, and then I sold the idea to BPDL's owners, and we made it work, right? And the idea, you know, because you still want to stay within a budget, was to rationalize the geometry and to bring more repetitions in the design. So the people living in the building, you know, they like it so much that they dress like it. So the main idea with something like this, and what's great about precast is that we can have this continuous insulation. Like we can really, from foundations to the parapet, you see, and we can really manage all the thermal bridges by insulating the connections. Now, you know, going back to Montreal, so I'm doing like the whole circus, I guess. I started in Montreal and basically taking those ideas that we developed throughout the years working in the city. So this is a building in Montreal that just got built, and if you look at the facade, what you see is basically those precast column covers going, you know, vertically all the way up, and a window wall in between. So when we looked at the design, we felt that it was really inefficient in moving back and forth from one trade to another. So we basically proposed to do everything with precast, so that there's only one trade. And the idea here was to play with two concrete colors. So, like a gray and a dark black color to create, to mimic the spandrels. So it's basically just a punch window design. And we basically reuse the idea of overlapping the joints so that there is no line in the middle of that pier. And doing a design like this, we basically saved 30% of the overall cost of the facade and not having to deal with two trades during the construction season as well. So sustainability. So when I prepared these presentations, I didn't have any slides about sustainability because for the last 10 years working in the city, the only thing that really mattered was money, what cost, and site logistics. So Russell was the one that says, Guy, you're not talking about sustainability. You have to put some slides in there. So, well, that's what I did. And the great thing is the industry of precast, the Canadian industry, has been working on this for some years. And the first thing that we did is, is you want to know where you stand. So we did an EPD and a life cycle analysis to evaluate what was actually our global warming potential. And basically the average that we got in kilo, everybody was talking about kilo and meter, which I was pleased to hear today, but we're basically at 260 kilo per ton, which per square foot translate into 8 pounds per square foot, or 90 kilo per square meter. I was listening to my friend Philipp Hofmann today and presenting some numbers about precast, but I guess, which were higher, but I guess in Canada we have the advantage of having hydroelectricity, which helps bring that number down, right? So besides the global warming potential, precast has a lot of advantages because it has a very low maintenance cost. Since we're working with large size panels, we have a great air tightness, thermal mass, and durability. So I remember, in 2012 when I started working in New York, Sandy hit the city of New York, and back then we were working on the Whitney Museum. So we had installed panel inside, panel outside, and the whole museum got flooded. But for the precast panels, all that water was just a walk in the park. So there was basically nothing happened. So this is something that we have to put in the equation, that precast is actually a very durable material. Now, can we do better? So if we want to reduce our carbon emission, we have to look at raw materials design, manufacturing, and installations. And the low-hanging fruits, for every one of those points is starting from the raw materials. Well, first of all, working with local supply of cement, but also aggregates really helps. Introducing recycled content into our mix. It could be the aggregate, but it could be silica fume, fly ash, to reduce the cement content. When we talk about design optimizations, a lot of time we produce panels and we don't really optimize engineering-wise, the thicknesses of the precast elements, but in many cases, the panel could be thinner. So we could reduce up to 10 to 15% the thickness of those panels. And then, installations, very easy ones. Like when we looked at site logistics, we're trucking panels to job sites, and a lot of time we get 2 panels on a trailer. Well, if we make those panels lighter and we get a third panels, then just by doing this, we're reducing our trucking emission by 33%, right? So from there, I'm going to pass it on to Russell.
Thank you. What's the advance? Hello. Just going to run you through a little bit of some of our history on research in precast. We see each kind of project that we do in the office as a movement forward, lessons learned, and then hopefully talk a little bit of a project we're looking forward to occurring here in New York. But as Guy and as Hill and as Chris is going to bring out, like, it's extraordinary what you can do with precast as a material. It's basically it's a form of the hand that's coming forward. And as I'm just starting out with a pretty simple project for us. This is over in Newark. It's basically a 1,400 linear foot wall that's holding back an electrical substation brought about from Superstorm Sandy. And I'm just starting out with this real simple idea that it's 1,400 linear feet. It's got some major security issues, protection of electric, of course. But the idea of using sort of the precast and very simply using the form liner to reduce the scale, to bring back the human notion, and then to play off, as you're starting to see, we've got some canopies in the front. If you look on the far right, you can see where we get some recycled glass built into that for a little bit of different texture. But the idea of looking at different forms and different faces and how that manifests throughout the project there. And then this is in New York right now. It's up in Sugar Hill. This was sort of a response to looking at the terracotta, a lot of the cornices that were of late 1800s being built in Uptown. And as we started to look at it and understand the terracotta as a process, and again of the hand and the craft, it became this question about actually manipulating the form liner. And you can start to see the image on the right if you step back far enough. I'm having trouble seeing it this close, but if you step back far enough, you're starting to see this idea of the ocular, the circular movements that occur from that, and then how it can manifest itself on the bigger building facade. And it's just, again, this idea of moving the craft of the precast forward, bringing it back and forward in time. And then we go down to Texas, where we studied just basically taking the same aggregate, same mix as Guy was mentioning. Everything's the same about this except for how we treat the surface, right? And using the lower portion of the building as more of a highly polished aspect, then taking that and making it more coarse as we move up, and then capturing the light from the sun in a different way. And then the Texas to LA, where we start to look at, well, polishing as a sequence is interesting, and we'll get back to that. Form lines are interesting, but can we move beyond sort of the traditional aspects of what we know of CNCing, form liners or handcrafting form liners, and go with something maybe a little bit more of character? And so what you're starting to see here is a precast that we had to work on, the technical aspects of how much you can have of open joint and open holes, so to speak, to capture water, and where that level can be, but basically using the idea of a spray foam in the form liner to actually give some of that texture that you're seeing in the dyed concrete. And then 130 William, which is right across the way here. And again, it's this idea of taking the aggregate, same paste, and now starting to use that to emphasize, right, and become the ornament, and work that in a different way. And you can see how we've sculpted around each window opening to make that a grander gesture. And of course, working that edge to get as much texture out of the face as possible. Which leads me to the Studio Museum in Harlem. It's on 125th Street. We've been working on this for maybe 5 years now. The border just opened up recently. We're able to get back up, get into Canada and see our first mock-up of this, and we're quite pleased. But it's a move to think about precast, again, in the same realm of what I was just talking about, of like how can we start to look at the same but change it ever so slightly. And what you're seeing here is one floor mock-up. This is sort of where the artist in residence would be operating on the 4th floor of the Studio Museum. And you're seeing basically these frames. And the frames come about from the vernacular of the brownstones. But what you're starting to see, though, is I think if you look at the top header condition there, you're starting to see that reflection, right? And now we're talking about the idea of reflecting the city a little bit differently within these frames as the opening of, say, brownstones. And then using the brushed or the the sandblasted areas around to create that moment of kind of falling back or the framing. As mentioned before, the process to how we got there was basically started looking at the base aggregates and having many conversations with Guy when we could steal his time to run through the studio. And that's kind of where, on what I want to feel like was a last-ditch effort by him, but very solid effort. You've seen that image here on the left here, where he actually came down from Canada saying, we couldn't find the aggregate you're looking for, but we found some big stone and we think we can actually get this stone. This is where Still is like, oh, brakes please. What's the PCI standard on this? How do we actually start thinking about this as a sacrificial layer that could be thought of? And so basically, to get this stone, and these stones, just for reference, are about 6 inches, which are quite a bit larger than your typical aggregate. But what it starts to do is starts to give you this new effect, right? And so it takes us a little bit back to the terrazzo feeling, but this is actually a precast product in which Guy and his team are handcrafting, hand-breaking some stone to get into this precast. And then you can start to see over here on the right this idea that as you start to model it, you put your reveals in, you can start to make these clean lines on sort of a more organic precast. And again, we heard it many times today, but it goes back to the craft of making the form, making the stops for when the large aggregate stops and when we start to turn the corner. You're going to see some of our formworks. Some of these are 3- and 4-sided pours, right? So we have to watch for what's the finished face on 1, 2, and 3, and then if it's a 4-sided pour, how much can we get out of the trowel, the hand, at that moment? But it's a process all along the way, from even the embeds and where the embeds go and the pick points for getting it in. It becomes very, very much a hand precision. Again, part of the issue on using this large aggregate that became part of the identity of the Studio Museum is that most of this stone is hand placed, which leads to a question when we start to put it on a whole panel about how to evaluate. Again, there's no PCI standard for large aggregates such as this, and how do we start to understand when the hand is okay as an art and craft, and when is it too far out of range? And that really becomes in the dialogue with the plant, and the plant managers understand the quality assurance, quality control programs, and being able to have those frank conversations where, maybe the hand got too far out of range there, or not. But it's become a sort of a real art project, and not so much of a production of a manufactured product that is standardized over time. One more image, right? And then the corner detail that where it's all becoming so precise with that formwork. You can see just that 3/4 inch as it meets the sandblast to the reflected there. And then lastly, I'm going to leave off with this image, but this is basically, I don't know, of the 200 panels, there's 50 of these panels that are 3-sided or more pours that we're anxious to see getting delivered to New York. And thank you for your time with that, Chris.
All right. So I realize I'm the anchor leg of the anchor panel, so I'll go quickly. I have about 10 minutes left. I'm going to talk specifically about 2 projects that OMA has done in New York that I've gotten to work on. OMA generally worldwide loves precast. It's on many, many projects. You can see them, but I'm just going to talk about 2 here. They're both residential developments that are in New York City. The first one is 121 East 22nd Street, which is not a Guy Tremblay project. It's done by Global Precast, so I'll go through this one fast. But this is a view looking down Lexington. It's at the corner, actually, of 23rd and Lexington here. And I'm going to talk a little bit about the design and how precast is able to actually reinforce our initial kind of formal concept and bring that to kind of final execution. So this site is a funny L-shaped site that is really kind of neither in Madison Square or in Gramercy. It's neither here nor there. And we thought that that was interesting, that the site really was either of no identity or 2 identities. And we also had this very strict zoning envelope, which you can see here with the need to maximize floor area, but also then have to set back at certain points for the street wall. And one place where you actually have some wiggle room in the zoning is the
corner articulation. And so we took that opportunity to actually reflect the collision of these two neighborhoods at this one intersection at 23rd and Lex. And so here is, let's see, a view of the project today with a distorted corner. And what you can see here and in this next image is actually these, the glass is quite successfully reflecting various points and images of the neighborhood, depending on where you're looking and where you're standing. And so you're able to get this mosaic of different perspectives of the neighborhood here at this corner. In this video, you can see that the precast is actually really just kind of slab edge covers and then framing out these facets of the distorted corner. These are stick-built precast pieces here. So we're able to employ stick-built at the corner and then move on to panelization as you go out to the ends of the facade. And one of the design moves here was to kind of grade away from this glassy corner and meet our neighbors, which have these very ornate classical punched window facades. And so we moved from this floor-to-ceiling glass into a more punched window vernacular as you get closer to those neighbors. And you can see that gradient here as you're standing on 23rd looking towards the corner. And this is really just playing with the proportion of precast to glass. And we did this by basically what we called, and we had many, many iterations that all required 3D printing of forms, and then it ended up being that we needed to do something with carpenters and 2x4s. So we simplified it to what we call pleats, and they're just basically rectilinear steps back. And we just increase the number of steps as we increase the proportion of precast. We use different finishes in which to create a kind of textural richness to the concrete. And here in this view, you can see as you go from the most punched window kind of traditional proportion and moving towards the glassy corner here. On 22nd Street, we have a much smaller frontage that's quite divorced from the corner. It's a narrow street, and we wanted to take some of that language but condense it in this smaller street frontage. And what we did is really create more of a three-dimensional undulation of the facade in this kind of tripartite form, and again using these pleats to help achieve that geometry. And so here a view, we kind of wrap around the School of the Future here, and you can see how we kind of meet our neighbor with this more traditional punched window vernacular, but in its own right quite contemporary facade that we think actually reinforces again, the overall formal move of the project. For this one, Greenpoint Landing, Block D, I met Guy in 2017 when he told me that precast could be done for very cheap and we could do it for about the same cost as window wall, and we were very relieved because we really didn't want to do window wall here. So we started talking back in 2017 with Sil, and very glad to be here today to talk about this project. I've been working on this one for about 4.5 years. Greenpoint Landing overall is a 22-acre master plan development by Park Tower Group and Brookfield. We're only doing the 2 towers at Block D here, which you may have seen going up. This is a rendering of it from last year. One of the key things that we wanted to emphasize with the proliferation of waterfront towers along the East River is to try and create some horizontality and actually reference some of the scale of the existing low-rise neighborhood as much as possible. I mean, it's a bit ridiculous to say it's contextual because obviously a 40-story tower is not contextual in Greenpoint, but we wanted to at least take some references or cues as we could. And so here, just taking this mid-rise neighborhood and just essentially taking those blocks and stacking them up. And what you can see here is a view down Eagle Street and how this scale is really just kind of repeated up the towers. Another contextual nod is looking at the existing facades in the neighborhood, and it's primarily a residential neighborhood until you get to the waterfront, where it used to be manufacturing. Of course, there's a lot of this kind of vinyl siding and shingling that happens on all of these buildings, and then we also thought it's quite interesting when you take a simple graphic pattern and you just rotate and orient it in a way where you create this kind of tension between these different orientations of the pattern. We thought was quite interesting, and we could use these kinds of rotations and the scale of shingles to maybe help create some articulation on the facade that reinforces the concept. So if we take a shingle and we rotate it and cascade it down the towers, block by block, you can create, again, this kind of moment of tension where it's really quite clear the articulation between one and the other with a very simple move. So that's a very bad picture of sand, but you talk a lot about sand and rocks when you're designing with concrete, because you, again, are trying to figure out how to create the perfect recipe, the perfect amount of sandblasting. Polishing, actually, as Russell was showing at the Studio Museum, is quite a bit more expensive than sandblasting, so really we only had a few kind of tools at our disposal. And Guy, again, very good with finding aggregates, and here he found us this red river stone that we thought was actually bringing a nice warmth to a white concrete that didn't feel too pristine or too precious. It actually gives it this kind of richness and a warm feeling. And when you put it on the tower on the rotated shingles, you know, when we were testing it to see the light concrete would actually capture the shadows as the sun moves around the project. And so depending on where you're standing and where the sun is, you get these tonal differences where the white concrete is really kind of absorbing the color of the shadow from a distance. And so these blocks are really quite reinforced just by the simple orientation of the shingle. So we did we got a mock-up delivered from Canada. We were super excited. We bought a time-lapse camera, and we set it. I spent a whole day setting this thing up, and we were so glad it worked, but also so glad the facade actually worked, and it was quite graphic, the shadows and the shingles, and it's really just 2 inches of material, 2 inches of sacrificial material that creates this really dynamic facade. And then this is a view probably 2 weeks ago of the north elevation, and you can see the 40-story tower on the right and the 30-story tower on the left. The cantilevers, of course, are maybe challenging. It's a total 48 feet of cantilever. So the structure was fine, whatever, they figured that out. It's also been quite hard to get the cantilevers, the panels underneath the cantilevers installed. So it requires a 2-crane system where you basically deliver it to a roof, an adjacent roof, and then there's winches that are basically on the floors up above each cantilever, and they pull the panel up finally in place, which is super fun to see, actually, and it's been just really exciting to watch come up. So that's all I have for you today. I'll give it back to Sil.
Okay, we have time for a few questions. So if there is somebody that wants to start, otherwise I'm going to go first.
Surely.
Yeah. New York City has some pretty stringent grading requirements. And given the sites we work on, not necessarily the large sites like a green site, and the buildings are being built without substantial tower cranes, do you see this inhibiting the future of precast in New York City? Does everybody hear me, or do you want me to repeat it?
I think better repeat it.
Hello there. Hi. My question is, given the stringent crane requirements in New York City, do you feel it's impeding the future of architectural precast use?
So, Dan, that's a good question because there's a lot has changed in the last few years, and mainly because of accidents that happened in the city. And the latest one was actually this crawler crane that tipped over. So when we saw the project, App 8, the design, it was actually designed and budgeted using a crawler crane in the street. And that crash actually happened in between, you know, and they basically had to change the overall site logistics and to put in a crane, a tower crane, to install the precast panels. So from what I understand is to be able to afford a precast, a tower crane on a building in New York, you know, it has to be quite a substantial project. Because those crawler crane, they've been building most of the precast schools in the city. Those crawler crane, you know, they've been building most of the precast schools and within the Manhattan area. We can still use them on some sites, but there's some there's some really tight restriction. So. I guess that really limits the scope of precast to projects with tower crane or projects where, you know, space is not an issue. So Greenpoint Landing, for instance, you know, we had 2 cranes two tower cranes, but we also, I say we, but there was also, a mobile crane used to clad the first 12 or 14 floor of the building. So I guess the answer is to go towards, maybe for the city of Manhattan, towards like lighter solutions, precast, like JFRC or UHPC.
Take one last question, anything? Right, I think we can close then.
Okay, are we done?
Just stay on.
Oh.
Great, thank you. You gave such a great presentation. There's no more questions. Or people are getting ready to enjoy the reception and are looking forward to a drink. So it was really, really very, very interesting, completely new aspects that I think the audience really appreciated. Thank you very much to the entire panel for your wonderful presentation. Thank you. So that brings us to the end of this conference. We are hoping that you enjoyed the presentations, the material that was presented to you. I personally found it fascinating, especially around those topics that are really relevant for the city and for our day-to-day work. But besides what we learned, it was great to have all of you here to be able to reconnect and to essentially mingle. I was reading one of these days that the innovation is much, much greater in cities, in urban environments. So the per capita innovations are higher. And the one and only real explanation is we as human beings love to mingle. And when we mingle with others, we become competitive and we exchange ideas. And that is one of the reasons why cities like New York, they will never experience a major shortfall. There will be temporary times where things look bleak like they did back in March of 2020, but cities always come back. And we as the facade community, we have a part in reshaping them and allowing them to reinvent themselves. So having said that, I wish you all a lot of success in what you're doing. Looks like we have a lot of work in front of us in the coming years, and we are looking forward to seeing you soon at the next conference. Thank you very much.
The mic on. Hello. Can I have the mic on, please? One sec, I'll just take a minute. So, a round of applause actually to Attila, our event host for today. Fabulous third time around. Thank you, Attila. Okay, thank you all for being present. I'm really sorry this took a little late. We had a production delay in the morning, but I think we did our best to make it up. So thank you all for being patient, and thank you all for being present in person. As I mentioned in the morning, we have 8 AIA LU CS CU credits assigned to this conference. So if you want those credits, please drop your AIA number at the registration counter at the bottom. We have streamed the whole event online, so if you can go to our website, facades.us.com. If you've missed any of the talks or would like to see them, they have been streamed online and they're available on our website. So that's with the streaming, and I'd like to thank our networking reception partner, Walter P. Moore. So the bar is open now. I hope to see you all over there. Take care and have a good evening. Bye-bye. Yeah, can I have a photo session with the panelists of this session? Can I have the photographer here, please? And Attila, if you could just come and join them here. Yeah.
Thank you.
Right, photographer. Yeah. Thanks.
It was great. It was really interesting.
Good.